of it. So it's one of the biggest institutes of the Max Planck Society. And we still have a legacy of Hoppe, and that's the Hoppe bunker. And I think Caroline went there a couple of times. And where we have normally our microscopes, and we are sitting, of course, with the offices and all the preparation tools in the C-wing. And the C-wing is occupied still by Wolfgang. He retired in 21, but still runs a group. Then John followed up in 21, and myself since 2002. And that's the famous picture of me smoking at somewhere. Summarize. So when I joined in 2002, I made up that slide. So it's a pretty old slide. So it looks new, but it's pretty old. But it's still valid. We have the hurdles in cryo-ET, and the hurdles are the samples itself. It's aqueous in nature, so we need to find ways of preserve the hydrated state. And what has already been mentioned for some preparation tools, like in the last day talks, high pressure freezing and vitrification. So there are still things which we need to consider and still to improve. It's not everything is at the moment really robust and reliable. It's in some of the cases it's like alchemy. And you need a green thumb for gardening as you need a green thumb for vitrification sometimes. And it's really an art. But everybody should be able to get good vitrification. Of course, we need also to improve the grid designs and make it more transferable between the instruments and microscope. For tomography, what's very essential is the sample thickness, and that's also like in transmission electron microscopy. If you come in material science or in life science, the same thing. You need to make your sample thin enough that you get to the highest resolution. And so we still have to advance sample preparation, FIB milling, and of course the 3D correlation. Otherwise, we don't know. When we heard Mark Ellisman about the multi-scale approach, we need to find means to correlate from the organism to the single cell to the molecule which we see in the end. Then we have low contrast, so we have to improve the imaging conditions by optimizing the instrumentation with faceplates, new detectors, whatever. So this is still ongoing work. So this is not like finished. You might say, okay, the detectors are almost perfect, but almost perfect can be better. Faceplates, well, they exist. We developed one in Martins Reed, the Volta faceplate, but it's still not like stable enough for longer operations, and it would be wishful that we have a faceplate which can be switched on with a push of a button, like the promises of the laser faceplate, for example, which we will see maybe in the coming years. So just follow up on that at one point. And of course the sensitivity, the chicken grill, we have to cope with it. So there's no way around it. We have to use low-dose methods and advance the automation and the acquisition schemes to get to the highest resolution. These hurdles are still present. And these hurdles in tomography are wrapped up in a workflow, which makes it even more challenging. And the workflow starts from the vitrification, transfer to the light microscope for correlation, transfer to the FIB for cryo-FIB milling, transfer to the TEM for tomography. So 3 transfers. Well, when we started in the very early days, like success rate of this whole workflow was almost 0. It was a pretty tough job to get it done. Nowadays, everybody more or less is doing it. One thing was to reduce the transfers, to combine, for example, the fluorescence microscope with the FIB. I will show you a little bit of glimpse into it, but Matthias Böge, who is following up, he will give you more details about that in the application. Then, of course, you need to improve the method and the technology and increase the throughput, because when we would like to answer physiological questions, we need to get statistics. And without statistics, we are lost. And in former times, we used 1 tomogram as a statistic, right? Grant Jensen is shaking his head, yeah, it was true. And of course, we need to improve image processing and make it more accessible. But what's normally really forgotten is improve the vitrification, and especially high pressure freezing technology. And you have seen that yesterday in John Heuser's talk about how old the technology of high pressure freezing is. It's a 50 years old technology, but it hasn't changed much. And still, like, mounting the sample in the high pressure freezer, that's the art. And that's done by everybody differently, meaning the outcome is differently. And so we are working on that part, as well as defining new vitrification protocols for samples. In 2010, we published a paper about our vision with the FIB. So take a grid, mill it parallel. That would, with a gallium beam, that would take days, even a week, because the gallium ablation of the gallium ion is pretty slow. So this is not an option. Then the wedge-shaped milling, as Mike Marco introduced in 2007, that's a possibility, but then it's also like difficult to reach inside the cell at specific positions. And then, of course, because I came from material science and I used FIBs, there is that lift-out approach. In material science, it's very common. You just lift out a sample and then attach it to a needle, or take a gripper, and then you lift it out and put it on a receiver grid. And when we did that in 2010, when we just only thought about what is potential possible, I said this will never be possible to lift out a cryo sample out of a frozen hydrated sample. I think this is not possible. And you should not say never. Never. I will show you a little bit into it. Okay, you know that we then lamella milling, no lift out lamella, but lamella milling on the grid, we introduced in 2012, and this is my last slide on the past. We published that paper about on the grid lamella milling, and then we had at 1 tomogram here in dictyostelium, and we did a rough average of that ribosome bound to a membrane. And then when we normally prepared the figures first before we wrote the manuscript, and then we gave the figures to Wolfgang for a double check. Do you like the figures? Could we do improvements or whatever? And then he saw that figure, and his statement was, and this is the original statement from Wolfgang, I just only put it because the handwriting is hard to read. I think this figure is a downer. The insert in A looks to me like a Gitan cryo holder viewer. I just only wanted to show you, like the ribosome, he didn't say the ribosome, he said the insert in A. So it was not a ribosome to him, it was more like a Gitan cryoholder. But since then, since 2012, a lot has changed, right? And let me summarize now that brief introduction into the past. In 2016, we had everything. So the combination of technology, meaning the accomplishments in hardware automation Titan cryos that took us more than 5 years, together with FEI at that time, to develop the autoloader and to develop the autogrids and to get it running without contamination. Contamination was an issue. Now we have an Aquilus where the contamination is an issue. So the history repeats, but we had it, and then we had direct detectors, we had the Volta faceplate, we had cryofib milling, and we had cryoclem. And then you see that beautiful image from the paper by Julia Mohammed on a HeLa cell where you look from the cytoplasm towards the nucleoplasm, where you can identify ribosomes that do not look like a side entry cryoholder, they do look like ribosomes. And you see the nucleopores, you see microtubules, you see the filaments, and everything in one snapshot. Beautiful. And when you now look over the past, when you look, I just only did a Scopus search on cryo-electron tomography, ion beam or lamella in the early days of this year, and you see that from 2016, it's almost exponentially how that application, how this increased in the community. And this is a success, and it's always rewarding to see people doing what we started to do in Martin's Reed and are continuing to develop it further. But now, en route to the molecular stories of 1001 tomograms. First, integration. So we worked, in this case, we worked together with Delmic, a small company in the Netherlands. And it's an old relationship I had when I started in Utrecht at the Bijwood. And so it's a wide field microscope. It's not like the best resolution, but it's integrated. And of course, there are other solutions like the PiScope from the Alex DeMarco lab at Monash and the iFlim now from Thermo Fisher, but that was a push by us to get like Thermo Fisher to develop because they didn't want to. And I said, okay, then I do it with Delmic. And then as it was running, they were coming and looking at it, oh yeah, we need one too. Now they have one. And they are similar in the performance. Both are wide field, so there are not big differences. It's in both cases you can localize your sample. And I'll just exemplify here on yeast. You see a typical contaminated grid for the focused ion beam. So, but it doesn't matter because you mill away anyhow at the agglomerates of the cells, like this yeast agglomerate. You just only have the FIB-SEM view here, and this is the direct view with the integrated light microscope, and you see the puncti already very clearly. Then you start thinning, and it's even get better. It's more crisp, it's more pronounced, because now the thickness is more homogeneous. And then you thin it down to electron transparency, and then you see that the thick material is now overarching in signal, but still you see the puncti. And then you transfer your sample to the microscope, you see the lamellae, you see the outline of the lamellae, you make the overlay, you see the two puncti, you correlate, and you take the tomogram. And this was done on the yeast, on the autophagosome in yeast, and they stained with EGFP, the ED1 complex, and they termed like that degradation compartment the end. Very good for the degradation of molecules inside the yeast. I didn't want to talk about the biology, I just only wanted to show you briefly, that's it. But it was a laborious thing. It's not like, the microscopy, yes, but the correlation you need to do by hand. So there was no software. So then we started to think, what can we do? And not only the automation of the correlation, but also the automation of the FIB milling. So we started to do a workflow automation software together with Julia Mohammed in Heidelberg. So with her team, we specialized on how to define software which we call serial FIB, like serial EM, serial FIB, so that you can also script and do your own protocols. It looks a little bit like the layout of the underground system of Munich, but it's not. It's like the architecture of the software. You have different use cases, so you can do on-the-grip lamellar preparation, 3D or 2D correlation, light microscopy, so independent of the sources where the data comes from. And then you have the FIB-SEM volume image in case you don't have an integrated light microscope or don't a confocal next, an offline confocal. And you can also do some automation for the lift out, and you can design new use cases and implement that in that software. The software is open source, meanwhile distributed to more than 20 instruments, even to plasma FIB instruments from different providers. So it runs now also on ZEISS systems. We are at the moment implementing for T-Scan, and JEOL is in process. So serial FIB will run, I guess, by the end of the year on all these different vendors' machines. A new use case was because one of the items which always bothered me, sitting at the microscope and telling the people, this is what you see, this is the image, and this is the sample, this is the best position for milling. But it's a lot of experience you need, which is the best position. And can we overcome this? Can we make a software which selects the position for the user? So you don't need to sit at the microscope and then say, okay, this is a good, this is a bad, this is a perfect position. And we thought about just only using machine learning, and actually Marina, she joined the lab as an intern and was keen on doing, well, it was during COVID, and programming and software development was her choice. And he said, okay, she said, okay, let's do machine learning. And so we defined the protocol. So we generate a scan of the grid. So we scan the grid with a low resolution SEM to get the positions. And then we use a network, a neural network, for segmentation. Where are cells, where is contamination, where are grid bars? And then we train, of course, with these images, the software, and in the end, it does it completely automatically. So the only thing what you have to do is to put your sample into the FIB and push a button. Perfect. Sounds like science fiction. Let's step you through that process. So you have an original image, which is pretty low contrasty, low dose. Okay, you don't want to spend too much dose on that grid scan. Then you do the semantic segmentation with the neural network. You see already like a little bit of grid bars and the colonies of the cells. Then you do a match with a library of templates for grids, because sometimes you use a hexagonal grid, sometimes a bigger square, sometimes smaller squares. But this you can more or less match with a template library. So this you can see here in yellow. You overlay that. And then you have, in this case, we just only colored 2. You have a blob detection algorithm. And I guess Marin will now shriek. Blobs we did in the past. Nowadays we do real high resolution. But in this case, blobs are nice to detect because they are easy to detect. And then, of course, you have 2 positions, like in this case. And a novice user, they would say both positions are equally well. Why would I not use the upper position? Because the upper position is lying directly on the grid bar. And that would take hours and days to get through the grid bar. And that was not what you want. So the software skips that position automatically and then proceeds to all the good position. And now fast forward. This is just an example from the plasma FIB, which I introduce in a second. So we use the model for which we had on Chlamydomonas reinhardi, that green algae. Saga introduced yesterday a little bit, which we trained on the gallium FIB, on the plasma FIB using xenon on yeast. And of course, the algae is almost similar in size than the yeast, so that matched well. So we didn't train the network, we didn't acquire any images, we just only did this grid scan, software, done. So we just mounted a couple of grids in there. 15 positions per grid were automatically milled without any user intervention. And it took for a couple of grids 4 to 5 hours, because xenon is pretty fast instead of compared to the gallium. These are just only some of the lamellae. They are not the super beautiful, but they are crisp enough to get decent data out of that yeast sample. And just imagine, you just only need to prepare your sample to do the vitrification, and then everything is done more or less automatically. This is the plasma FIB Saga shortly introduced, and I just only used that movie from Thermo Fisher to get you a glimpse on it. So together with the Rosalind Franklin Institute and Thermo Fisher, we started to develop a FIB with a smaller chamber, so to reduce the amount of contamination, with a higher automation, so to make it more compatible to the Titan cryos, so it has an autoloader, and with an integrated light microscope, where eventually, well, it's bottom placed in that movie. You can see that the light microscope comes from the bottom. At the bottom there is a lot of space. Even you could accommodate a confocal or maybe a super resolution microscope. So just need to think about like the application in the future. And with a special stage where you can mount directly the order grids, which are stored in the 12-fold storage positions of the cassette. That's the plasma FIB. This is like a early day image of 2 different prototypes, which we used in the factory. You see on that side, you see the autoloader, you see that chamber. It looks more like a soccer ball. It's highly reduced. And in size, it's not like for that 8-inch wafers. It's like really specified for the small grids. What it does not have is a lift-out system for doing the lift-out. But Let me show you some of the data. We just use here a high pressure frozen waffle. So it's a defined thickness. It's not 200 micrometers. It's like the thickness of the grid which we used at 30 micrometers. It was a hexagon grid, and we just used xenon, and 30 micrometers, 50 minutes per lamellae. So it's on the grid lamellae, so to speak, but on a high pressure frozen sample on that fib. And so you get pretty fast to thick layers of ice, and you get decent quality. However, lift out is not yet incorporated. There are different plasma fibs where you can do it, but we are working on maybe a liftless approach. Let's see. But now to the almost impossible, which I said, I doubt it that it ever will work. So in 2013, we already started with the lift out in the factory. And this is also like a contribution to the long and winding road. And during that lift out in the factory, it was the first lift out ever made at cryo. I was together with Julia Mohammed for 1 week. And at the end of the week, we had success. So we transferred the sample to the microscope, took the first images, heavily contaminated, but we could see something. We couldn't do a tomogram because the sample was lost in the night afterwards. And at the same day, FEI came to us, or to me, and said to me, JP, you know, we are now stopping all FIB development for cryo. That was like a bummer. We just did the first lift out. We worked hard to convince them to build a machine for cryo fib milling. And then they came to me because they said, we need to save money for getting higher share values. And this R&D is consuming too much. It took 2 years to convince them again to restart the program. Of course, in 2015, we had the first prototype. In 2016, we had, similar to the Aquilus today, a system. And then now we have that system. So it took quite some time to get them going. And in 2019, we just only continued with the development. I said, I don't care, to be politically correct. I don't care what FEI is doing about their shareholder values. I'm doing the development. And so we started together with a company called Kleindig, an old friend of mine from the physics department in Tübingen. He founded a company doing micromanipulator for FIBs. And I said, well, why not do it for cryo? And that was the start. And we used C. elegans, and you see C. elegans would be way too big to get going in a normal fashion, and also in the gallium fib. You do the correlation to define the area where the embryo is in the gut regions, for example. And then that was the idea. That was just a movie Oda did. At that time, she did her master studies in Martinsried. And we use a gripper, like a tweezer. We mill in trenches, and then we grip out a little lamellae and put that little lamellae on a receiver grid. Where you see already, like in that movie, there is a mistake. I will show you in a minute which kind of mistake that is. You put that in a receiver grid that has pillars, and on these pillars there are slots, and then a little lamellae can be placed in. That was the vision. And that was the reality. So first of all, this is a high pressure frozen sample. And everybody of you can see C. elegans. No, of course not, because it's hidden. You need to have correlative means, so you need to have the fluorescence signal. And now you see that's the location which I showed already in the overview. It's the same fluorescence signal. Then you take the gripper and you have a really tiny lamellae. And with piconewton forces, you grip it and then you place it in a modified slot. Has to be much, much smaller than in material science. You coat it, you thin it, you polish it, and then you transfer it to the microscope. It worked. So a little bit of contamination attracted. The crack you saw, the tomogram, one of the tomograms, we took 5 tomograms. Okay? That's not really high throughput. We did 3 lamellae. So you can just imagine. And we took a couple of weeks of time. And then we analyzed the data, and when you look at it, you see a little bit, oh, I was a little bit too quick here in this case. You see some details, like one-coated vesicles, you see microtubules, and you see, of course, ribosome and other structures. And we just only said, let's hunt for the ribosome, the classic, and see if it looks different than a Gatan side entry holder. Yes, it did. In this case, we could distinguish 2 states of the translational elongation cycle at 11 or 12 and 15 angstrom, and that was an achievement. So we had a nice publication, but it didn't work. Not for the community. And Carsten Sachse invited me a couple of years ago to the PICO conference, where the material scientists normally talk about aberration correction microscopy, and he wanted to give me a statement about what's the state of the lift out. Can we use it? Is it ready for liftoff? And I said, no, not really. The problem was that little lamellae, which we prepared over days and put into the slot in the receiving grid, that receiving grid was not pre-clipped in an autogrid. Because of the geometry of the slots, you had to get in from the top with the gripper. Also with the needle, you had to get in from the top to get it into the slot. And so you couldn't do a pre-clipped autogrid. And so clipping these delicate and fragile lamellae was pointless. Like you lost all of them. 0 success rate. And of course that was a lot of criticism in the community. What can we do? Now let's wrap up. Do I still have 5 minutes? Okay, good. Now let's wrap up. So what we first used were these bare grids, not clipped. You see these were omniprobe grids from former material science, which I had in my drawer. So we had these pillars, and then you created the slots on the pillars by platinum deposition at room temperature. And then you can place a very small lamellae in there. Second idea was to pre-clip into these half-moon grids where you have freestanding pillars, but then you have to have a means to get the lamellae glued to these half-pin pits. In material science, very easy, because you use platinum deposition at room temperature, guided by the gallium beam. You just glue it. And it's very well known that you can deposit the platinum and glue your stuff at room temperature there. But at cryo temperature, you can't use that. Site-specific deposition is not possible with the platinum. So we had to find another means, and we found one means, and I'll show you in a minute in a movie how we did that. So by redeposition material from that copper pin onto the ice block, we could weld the ice to that pin. And second, we could extract a much, much bigger block to guide a little bit the milling and the position on our high pressure frozen sample. So we had 2 things. First of all, from the small lamellae, which was pretty delicate to handle, we go to a bigger block, so increase the size from 200 cubic micrometers to 6,000 cubic micrometers. We have lots of more material to guide where we would like to have our lamellae out of the high pressure frozen material. And we can pre-clip the grids. Already the success rate was higher. Second, when you have it like this in this geometry, you can mill with the gallium beam from the top. You can image either with the light microscope or with the SEM. You can do slice and view, so to speak. And when you have then defined after a couple of slices the position where the biology is, which you are interested, then you just, as in on-the-grid lamella milling, you mill from the bottom. And then you preserve the biology in the thin lamellae. It's compatible with the gripper or the needle. So these are just 2 examples where you can see. You see also like here this regular line pattern, how to redeposit the copper onto the ice block. You can also see that it's not like a huge lamellae, because it's single-sided attached. You can't make it 100 micrometers long. It will bend at one point, so it's not very sturdy. So it's only 20 microns or even less. And now let's look into the movie. You see here, in this case we use the gripper. So we do the trench milling. And it's much easier to lift out a big block than a small one. And then you weld it, so you create a line pattern. You see that, tuck, tuck, tuck. So, and the copper is deposited on the ice and welds the ice to the copper pin. And then you have it, in this case, like a standard half-moon grid where you have 4 pins. As in material science, you have 4 blocks. And now in this case, we didn't use the integrated light microscope. We just used the slice and view. Just wanted to give you, and that's implemented in our software, which I showed you. You see the lipid droplets. This is like a slice or block which we made from Drosophila egg chamber. So also a big unit. And I let the movie run, just wanted to give you a glimpse how it then looks in the single-sided attachment. So we cut away the leading end, the front end, just to prevent a little bit bending. We zoom in. You don't see gold particles. These are now fiducials. This is platinum aggregated. And we had a discussion yesterday with Mark Ellisman about how this happens. And then we do the tomography on that Drosophila egg chamber. However, when we had that already technology in hand that we can lift out a bigger block, I said, why not lift out a huge block? Like a block containing a whole C. elegans worm. So that was the idea. And then slice it, thin it, and put it on a grid. No specialized half-moon grids, no specialized slot grids, just a normal, regular, as in old times. I can imagine, Grant can remember the 100, 400 mesh grids which we used to get a little bit more tilt freedom. And I had a couple of them still in my drawer, and so maybe that would work. So only with one lift out of one block, you create lots of slices of your worm. That was the idea. We did it, of course, that was, you can look at the date, it was May last year. That was the first attempt in summer. A block 150 micrometers long, 65 micrometers in width, and 20 micrometers in thickness. So it was a waffle, not a 200 micrometer high pressure frozen sample, but a waffle high pressure frozen sample of the C. elegans larvae, not the hot adult worm. And what we did, correlation, did the trench milling, and then, to make it more sturdy, we created a handle. Like we sacrificed a little bit of the copper of the grid material, which we welded onto the block to make the transfer more sturdy. Then, in this case, we had to shake it a little bit free because we were not very precise in milling it free. So shake it, baby, and then it's out. And then you move it, turn it. In this case, we use single-sided attachment. So you place it next to the copper pin. You create a line pattern to glue the block tight, and then you cut a slice of 1 micrometer. And then you go to the next pin and do it again, and do it again, and do it again, until you are finished with the block. And just let it run so you can see. And we just use the regular grid in this case, which we cut open to make that half or that single-sided attachment. In this first case, we created, I think, 20 to 25 lamellae, which then have to be polished afterwards, and then did tomography on it. As I said, this is not, we can't do a super wide lamellae because the single-sided attachment tends to bend and we reduce the material. So the idea came up to do double-sided attachment, as I showed in the sketch. And that's the movie for the double-sided attachment. So we just only give you a glimpse. Again, the same thing, the copper handle on a needle. It's a huge block. You do the correlation, in this case, with the integrated light microscope, you see the beauty, overlay it, there we go. That's the larvae, nicely preserved. And here in that movie, it's not really nicely visible where the block is, so it just only, you see the 100 by 200 mesh, you see a black block, like from 2000 Space Odyssey, like the monolith, which is placed on the grid. You do the welding, the cut, next, welding, cut, next. And in principle, you could do now really elongated lamellae. I just shortcut now to show you the grid after coarse milling. That is roughly 18 hours of work, 40 lamellae. So you need to have like a FIP which runs for 18 hours, so this is a little bit of a challenge. But of course, when you have like automated system with automated cooling, that would help a lot. So it all looked clean and nice. Then the next day, so you had to take the grid out. The next day you come again for the polishing, so you attract a lot of contaminants, and of course, sometimes you lose some of the lamellae, so out of 40 we lost 2. And then we transferred to the TEM, and during polishing we also were over-eager, so 2 of the lamellae were shot through, so we were too thin in the end. And so in the end we only had 35, and I just give you a glimpse into it. This is one of the sections, one of the lamellae, so a cross-section of C. elegans, and you just can compare it to the anatomy, which is of course in the atlas of the C. elegans. I'll let John take a picture, good. Just look at the tomography you can now obtain. This is the body cell wall, the muscle cell cross-cut link on the left side, the tilt series on the right side, the tomogram. Of course, we did that for different parts of C. elegans, and I just need to tell you, 1,200 tomograms were taken on these 35 lamellis over Christmas, so we did that experiment just before Christmas. And then we used 2 microscopes to acquire 1,200 tomograms, which we still analyze. So this is just, we place the sections into the cuticle of the C. elegans, just to give you an idea where they are. They are not serial sections because we lose material in between, but you only do 1 lift out, right? 1 lift out, big block, and then you just do the lamellar milling. So the time consuming and most delicate step is reduced to only 1 step, and that made it work. And the question was, of course, will this yield structure? And of course, what we normally use is the ribosome. And I just show you, this is the first sub-nanometer ribosome structure of C. elegans. So it's not the first C. elegans structure, but it's the first sub-nanometer structure. On lamellae, which were not super thin, they were like in the range of 300 nanometers. And we could define even some of the classes of the elongation cycle at different resolutions, of course, but it's fantastic what you now can do. When we submitted to Nature Methods, of course, the editor immediately said, you need proof of a second structure. The ribosome is not good enough. Yeah. What we did, we found some microtubules. And the beauty is, just look at the tomogram. You see on the right side, you see that neuron with a lot of these microtubules, and you see epithelial cell with only 1. And then you look closer, and you see 11 spokes in just 1 tomogram. You see the 11 spokes and the 15 spokes, which are, of course, the 11 spokes are quite common, while the 15 spokes are only sparse. But now you can mine the data to get more information, and these are 2 different cells, of course. That's molecular structures in cellular tissue. And now you can think about what can be done with that technology in hand. And with that, I would like to finish with a statement by Sidney Brenner. Well, first of all, I would like to thank all the people who worked on that stuff I showed you today. So it was not only, as I said, 1 person, there was many, many persons involved, and also like with the help of industry. And I just read that statement by Sidney. Progress depends on the interplay of techniques, discoveries, and new ideas. Probably in that order of decreasing importance. And before I leave you now for the discussion or for the questions, I just only let in the background run the movie of the sections to just only to marvel a little bit together with me on what you now can see on a cryopreserved specimen of a whole organism in cross sections. And we just only zoom in to different parts at these different sections, which we are still analyzing. And we already gave like 200 of these tomograms to Chan Zuckerberg for a data portal so that machine learning people can use it for getting maybe faster annotations and faster tools for mining that data, because one human being, as I said, is not enough to analyze the data. And with that I close, and I thank you for your attention.
Thanks, Jürgen, for the beautiful, beautiful work. So we have time for questions.
Beautiful work, indeed, and beautiful historic pictures and movies. I was absolutely fascinated. I was wondering, if you have such a big structure, then you cannot just do a 3D reconstruction of the whole structure, because there are local alignments in all these different. Whatever you do in terms of 3D reconstruction will be a local 3D reconstruction, or do I see that incorrectly? And immediately attached to that is FEI was at the time when they were just marketing their tomography software. They had some very weird, how do you call it? Algorithms in terms of exact filters or not filtered and iterative things, and they promoted the iterative beyond the more linear algorithms. I haven't followed that, but maybe you can just update my knowledge there.
First of all, to clarify, maybe you can omit that by over tilt and under tilt so that you get it homogeneous, but there is a 7-degree tilt of that lamellae which is welded to the grid. However, it's pretty homogeneous, so you can take out of one lamellae a lot of tomograms, so this is really nice. But you can't stitch them together like in a montage. This is, at the moment, really not possible. Maybe at one point. I will not say never, that will never be possible, but it's a little bit tricky with the dose distribution and with the overlapping regions. However, of course, you can do, like now, focus on specific region into your C. elegans, for example, into the gut region, and investigate really the cell-cell junctions. So you can make the slices even thinner. So we explored not to use 1 micrometer slices. We explored to go below 500 nanometer, and I think it should be possible to get down to 300 or 200 nanometer with special beam shaping methods. And second, for the analysis of the tomograms, we of course don't use Thermo Fisher software. So it's like this was all assisted by serial FIP. There is no, the operating system of the microscope is involved. For the acquisition of the data, we used Tomo 5 from Thermo Fisher. That was working well. And for the analysis, we used our homemade software, and as you have seen yesterday in Saga's talk, the Tomo Man from William 1, which we modified a little bit to have a pipeline. And at the moment we are streamlining that so that you just only have a Python user interface to put in your values and the data, and you just let it run. Just this is a comment, but you can't really reconstruct the whole worm. This is not like what we aim at to compete with stereo sectioning. but I can think about John can marvel at the idea to have now a high pressure frozen sample at molecular state. I think that might be great.
And John has a question, but before, just want to ask, do you pay yoga classes for your staff and students?
I just wanted to ask, have you got on your phone yet the roadmap from Martinsried to Stockholm?
I don't think so.
I think you'll get there.
So any additional questions? Yeah, Moira.
Hello. I'm curious if you tried some developments about the vitrification with clipped grids. And also I want to ask you if your 3D clamp, you use some fiducials or if you can apply our regular image from the cryolite, or if you need the confocal.
We are trying to do some stuff with, not with liquids, but with microfluidic devices for the vitrification. It is way too premature to tell you anything about the success. I hope that by mid of next year, beginning of next year, we have some proof that it will work. That would omit a little bit like the alchemy, also for bigger stuff. I am not aiming at like 200 micrometer thick slabs, but maybe like a larvae of C. elegans with 20 to 40 micrometer that would be suitable for that vitrification technology. Second, fiducials, yes. The common line of to do the correlation is with fiducials, but in very special cases, when the biology has enough features, you can also use the features of the biology to do the correlation. That helps a lot, but it's not in every case, so you have, it depends really on the biology sample which you put under the confocal microscope. And at the moment everything is offline. Of course there are approaches for structural illumination microscopy inside the FIB. There was one publication by the people from Beijing, but they use a side entry cryoholder, not the ribosome, but a side entry cryoholder, which I found not so attractive nowadays. But I think from the structural illumination perspective, this could be implemented in any kind of FIB. I think this should be explored more, and people are working on super resolution like Peter Dahlberg in Stanford and Rainer Kaufmann in Hamburg. And we are in close relationship to the people. Just as soon as they have something which we can put under our FIB, we go for it.
Okay, Jürgen, thanks for your wonderful lecture. I have one question and one comment. The question is, did you check for the quality of the freezing for this whole xenohabitates? There are areas where there is problems with the frozen process.
You see, I didn't mention that, but the protocols which have been defined for high pressure freezing on these systems have been defined for freeze substitution. So they never really were interested in the molecular structures, but they were interested in preserving. But they also didn't bother if there are some areas which are not perfectly vitrified, because it was freeze substituted anyhow. Mm-hmm. Now we found out that we use the same protocols and you have incomplete vitrification, because you see that in the TEM slices of this material, but only after you put them in the TEM. Can check the quality of the ice. So a quality check can't be done beforehand. Mm-hmm. So this is also like a little bit the problem. And so we have adapted the protocol over 6 months for the larvae to get it really vitrified. Mm-hmm. Then we tried to get it for different stages of the C. elegans developmental cycle. Mm-hmm. And we even achieved now halfway good ice for the adult worm. Mm-hmm. But it's a tough job, mm-hmm. And the Drosophila was the same thing, and Matthias will show you also like his material, which is a different story. You need to adapt the protocols, and you have no guarantee that in every case and in every instance it will work out. Mm-hmm. So this is very, very complicated.
Okay, in relation to the comment, appreciate very much your historical introduction. Yesterday I mentioned that 1954, yes. Humberto Fernandes Moran worked at this institute for almost 1 month, together with Maurice Wilkins from UK that got the Nobel Prize for his work on X-ray diffractors. And they work on frozen samples of the electric fish and did light diffraction of the electroplates. They never published it. Probably the results were not good enough at that time, and we could not recover all this historical material. But anyway, it's important to mention that in our institute, Mauricio Wilkins and Humberto Fernandes Moran worked together and became friends for the
That
whole
I didn't
life.
know, but that's very interesting. Thank you very much.
So with that, we move on. Thank you again, Jürgen.
So, good morning. We will start the second talk of the day. And we have here with us Dr. Matthias Poj. He made his PhD at Martins Reed, supervised by Professor Wolfgang Baumeister. And then he is a postdoc at the same place, at the same lab, and he will present his work for us today. Thanks, Matthias.
Yeah, sure. This rather short and unspectacular CV gives me actually more time to talk, right? So not so bad. And I'm really grateful for the opportunity to be here. Thank you very much also for organizing this symposium, bringing us all together. It's really great. And yeah, after Jürgen gave us already some beautiful introduction, also in the historic context what cryo-electron tomography is, I would like to show you a few more examples how we use cryo-ET to look into cells, or in some cases even between them. In any case, initially I would again start with a rather lengthy introduction, how I perceive cryo-electron tomography, why we like to use it to peek into cells, even though it has some disadvantages. And this is maybe also for the students in the room, because you are going to use this technique, and I feel you should know the concepts a bit more. Then I would like to proceed to how we study the architecture of the rod outer segment in mouse, and how we image the interface between moss cells. And in the end, I would like to explain you why I actually am allowed to be here amongst so many very accomplished scientists, and also give you some examples of some serious blobology. But let's start with the introduction. Cryo-electron tomography. That is, in my opinion, actually quite a tough word or name, but it describes fairly well what we are actually doing. In fact, many people in the field prefer to call it electron cryotomography, because cryo-electron gives you the idea that our electrons are cold, but that is actually not the case. In fact, we are accelerating down the column with 300,000 volts. They're actually traveling down with faster than half the speed of light and have quite some kinetic energy. And at this speed, they have the wavelength of about 2 picometers, which is orders of magnitude smaller than visible light. And therefore, as a rule of thumb, the smaller the wavelength for imaging is, the more details we may be able to resolve. And in the case of transmission electron microscopy, we may actually be able to resolve the molecules or even the atoms in our sample. However, so we do transmission electron microscopy, that's why electron, but using electrons for imaging, especially for biological samples, comes at a disadvantage, because these high energy electrons interact extremely strongly with matter. So if we look what is happening in a TEM, we have some electron source here, and we illuminate area on our sample, collect the electrons passing through the sample, and image them on the detector. And if this column that is actually quite high in this beast of a microscope that you see there, if it would be filled with air at normal pressure, all the electrons would be scattered way before they even get close to our sample. So we need to have the column at an ultra-high vacuum. And that is really problematic for biological samples like cells because they are mainly composed of water. So if we would place our cell in this microscope at this ultra-high vacuum, it would dry out immediately or simply explode. Really bad if we want to image intact cells, right? So somehow we need to fix the samples or the water in the samples. And on the other hand, our samples need to be extremely thin. Only a few hundred nanometers. If they are thicker, not enough electrons are passing through the sample that we can image them. So yeah, what people traditionally did actually, they fixed their cells by cross-linking the cellular components. Then they infiltrated or replaced the water with an organic solvent, then stained the complexes or structures they were interested in with heavy metals, like the membranes. And then they embedded it in a resin that forms a plastic-like substance after it solidifies. And these samples are actually fairly easy to handle. You can cut them in nice thin sections for transmission electron microscopy, and you can do all these things at room temperature. And as you can see here, they have this amazing contrast. And these images actually really shaped what we know today about what is happening inside cells. They, for the first time, opened a window into the cell. But this is not a perfect preparation method because it introduces artifacts. So as you infiltrate the cell, you move things around, membranes get all wiggly, and you denature the proteins inside the cell. And especially, you're also not imaging the biological structures themselves, but rather the metal coat surrounding them. Another option that we have is the cryofixation. You may think if the problem is the water in its liquid state, why don't we bring it into a solid state, like just freezing the sample? It also doesn't work that easy. I mean, if we could just put our sample into the freezer, but then it cools down extremely slowly and ice crystals are forming. That is also bad because they have a lower density than the water before. So ice crystals are expanding and therefore also destroy the structure that we are interested in. For example, you take a strawberry that is nice and stiff, then you put it in the freezer and you take it out and thaw it, and then it's all squishy, right? Because ice crystals, as they grew, they destroyed the cellular structure that we are actually interested in. So what we need to do, we do a so-called cryofixation where we very quickly cool down the sample below minus 150 degrees Celsius under conditions where no ice crystals are formed. And in this case, we then basically trap the cells with all its components in a vitrified or glass-like state. Yeah, that, of course, again, comes at a serious set of disadvantages because these samples, after cooling them down, we must keep them below minus 150 degrees Celsius, otherwise ice crystals can form again. So we need to store them cold, thin them down cold, and also image them cold, which makes the handling difficult, and you need very expensive equipment. And on the other hand, these samples are very radiation sensitive. So as we image them with the electron microscope, we start to burn it, meaning we need to extremely reduce the exposure time that we use here, which makes the images noisy. And we don't have any heavy metals in our sample. Therefore, we also don't get contrast, or not so much. So if you look here, the untrained eye may not see anything at all there, right? But on the other hand, this preserves our cells really, or the structures we are interested in the closest to native state that is physically possible at the moment. And also, this is, really the best preservation that we have at the time. Yeah. And we have two possibilities for the cryofixation these days. One thing is the plunge freezing. I'm not sure whether I should talk about this a lot. But the idea is if you have a sample that is thin enough, then you plunge it into a cryogen, like liquid ethane or ethane propane. And if the sample is thin enough, then it can cool down your sample so quickly that the ice crystals have literally no time to form. If your samples are thicker, however, we need a different method, and this is the so-called high pressure freezing that Jürgen was already talking about. What we do there in the commercial systems that are available these days, we have metal carriers of varying sizes, and there is a little well in here. And then you fill your sample into this well, place another carrier on top, and then you inject it into this high pressure freezing device, into a pressurized chamber where there are actually 2,000 bar of pressure applied to the sample. That may sound weird, right? 2,000 bar, will that not destroy our sample? Actually not. If there's no air in your sample, it's liquid, then it's in a good approximation incompressible. And the pressure also comes from all sides equally, so there's actually no deformation in your sample. And under these 2,000 bar pressure, ice crystals want to expand as they grow, and this high pressure somehow counteracts the growth of the ice crystals, and therefore we are able to cool down our thicker samples, even at slower cooling rates, without ice crystals forming. What is a thick, what is a thin sample, you may wonder? It always depends a bit on your system, but as a rule of thumb, for plunge freezing, if your cells are thinner than 6 to 10 microns, you can use this. Beyond that, you may need high pressure freezing. Then we still have the problem that we need extremely thin samples. And again, as a rule of thumb, if your sample is thinner than 500 nanometers, you may be able to image them directly in a transmission electron microscope. And beyond that, you need to do the thinning. Jürgen also presented already very beautifully the method that we like to use in our lab, which is the focused ion beam milling. So in this case, we load our samples into a little shuttle like this, and then into this dual beam focused ion beam setup, where we use the focused ion beam from a shallow angle to deplete material, and with the SEM, we image from above the progress. But again, our samples need to be very cold at all times, so we actually mount them under liquid nitrogen into this shuttle and load them on a stage that is cooled by an external cooling system. Yeah. Just a little video how the focused ion beam milling works. We actually define patterns for the focused ion beam above and below an area of interest, and then we continuously scan only these patterns. And as we scan with these high energy gallium ions over our sample, we start to remove material. And this is how we are then left with only this very thin sheet of material that we call a lamella. Okay. That being said, so we have electron and we have cryo. The last part that is missing is the tomography. And the images that we acquire in a transmission electron microscope are in a good approximation, two-dimensional projections through our three-dimensional sample. And they can actually heavily trick us, like the games of shadow. If you project your hand at the proper orientation against the wall, it may appear like a dog or a goose, but of course our hand is not a dog or a goose, right? So it can really trick us. Another example that I really like is photographs are also only two-dimensional images or projections of our three-dimensional world. So who believes that this is a double-headed rhino? Probably no one, right? Because our experience tells us probably these are two of them, but they are just standing at a correct angle behind another that they appear like a double-headed rhino. But when we look into a cell at a structure that no one has ever seen before, we really must avoid these misinterpretations of two-dimensional projections, right? So here what would help, just taking a step to the side and taking another picture, then we would probably resolve that this is actually really two rhinos just behind each other. And we do something very similar in a transmission electron microscope. We basically tilt our sample with respect to the electron beam and acquire these projection images from a set of different angles in a so-called tilt series. And then we can use three-dimensional reconstruction algorithms to get a three-dimensional representation of our sample, which we call a tomogram. And by now you may have guessed it, this also comes with a set of disadvantages, because our cryofixed samples are extremely radiation sensitive. So we have only a limited exposure time, which creates noisy images, and now we need to split this limited exposure over 30 to 60 images, which actually makes everything only worse. This is a picture of my boss, Wolfgang Baumeister, and if we would now acquire like 36 images with an increment of 5 degrees between plus and minus 90 degrees, so every black line here is a single image, and then we do this reconstruction, he will get quite a bit distorted. But that is not everything. Unfortunately, the samples that we use are usually these thin sheets of material. And as we tilt them with respect to the electron beam, their effective sample thickness actually increases. So beyond 60 degrees, usually the samples become too thick to allow imaging in a TEM. So effectively, what we have there is a wedge of missing information that is called the missing wedge. And that really heavily distorts the image now. And again, everything is very noisy because we are limited with the exposure time. So if we add the noise from here to here, I mean, I may recognize that it's a human being, but I don't really recognize my boss anymore, right? So yeah, this missing wedge. And at this point, you may say, cryo-electron tomography, that sounds really like crap. I mean, we have extremely difficult to handle samples, we need very expensive equipment, and in the end we get extremely distorted and noisy images. Why the hell would we ever do that? And this is exactly what people told Wolfgang Baumeister years ago when he decided to focus on cryo-electron tomography. And it took really years of hard work, lots of technological advances, many of them done in Baumeister's and Jürgen Plitzko's lab, to get at a point where cryo-ET is actually useful for cell biology. And in the following, I would like to give you 3 examples that this is actually true. So I hope by the end you believe me. Yeah, there's one more concept that I would introduce you before, subtomogram averaging. I think you heard about it a lot during this symposium already, but what is it actually? So initially our tomograms are really noisy, and also they are distorted due to the missing wedge. But quite often we find complexes several times in our tomograms, like here marked by the yellow arrow, the proteasome. In different orientations, the proteasome is a machine that degrades misfolded proteins in our cells. And then we can cut out small subvolumes or subtomograms around these positions where the proteasome is, and then start to align them with respect to each other and average them. That's why the averaging of subtomograms is subtomogram averaging. And in doing so, what is happening, we are actually averaging out the noise that we have in the raw data, and we recover high resolution or details that were buried under the noise before. So we can really recover higher resolution information from our raw tomograms. And afterwards, we can also classify them, meaning we try to find different forms of the proteasome. In this case, they found some of them had a double cap or a single cap. That is a structure involved in substrate recognition. And even different processing states they could identify for the proteasome in their cell. And then they can analyze their distribution in the crowded context of the cell. And in my opinion, this is a super powerful thing to do, and it's only reliably possible with cryofixed samples, in my opinion. Okay, that was the lengthy introduction. Let's move on to the project where I was working on in my PhD, and that was the architecture of the rod outer segment in mouse. But let's start like this. Our eyes are really remarkable sensitive detectors for light. Even a flash of one single photon is very likely to be registered on our retina, which is the light-sensitive tissue on the back of our eye. And we have 2 different types of photoreceptor cells that we are using to see, actually. The cone cells, these are the guys that we are using right now for the color vision when it's bright. But when it's dark, we actually rely on the rod photoreceptor cells, and these were the guys we are working with. This is a sketch. They have an inner segment, a cell body, a synaptic terminus, but we were interested in the rod outer segment that is connected via a thin connecting cilium to the rest of the cell. In the rod outer segment, this is actually where the light signal is converted into a neuronal signal. And in mouse, it is actually composed of a stack of 800 membrane disks that are equally shaped and precisely spaced with respect to one another. It's really like bilayered vesicles that are squeezed until you have 2 parallel membrane planes that are surrounded by a high curvature disc rim at the edge. If you look from above, they have a diameter of about 1.3 microns. And another feature that they have is this little gap into the disc, which is the so-called incisor. And yeah, the machinery used to transform the light signal to neuronal signal is actually sitting between those disc membranes and the cytosol. And please don't remember all these things, just remember that there's lots of proteins swimming around there, okay? Yeah, and what we did, we isolated the retina from mice and vortexed it. And doing so, the rod outer segment would be pinched off of this connecting cilium here. And then we basically had them in solution. These round things that you see in this light microscopy image are cell bodies, contamination that we actually don't want. But these elongated structures that are all over the place are rod outer segments. And then we did the drill with the plunge freezing. So we just added them to a grid, plotted away the axis of buffer, and plunged this. And then starts the FIB milling part. So we load them into this shuttle. And this is a camera on one of our FIB systems. And this is from the loading position into the normal FIB milling position. Unfortunately, here we only see the S of the shuttle, basically this part here in the back. But in the sketch, you see better that here, with the focused ion beam, we come at a shallow angle to millamelle, and with the SEM, we look roughly from above onto our grid. This is the grid overview. This is not how your grid should look like. You should always grab it with the tweezers at the edge, but obviously I didn't manage to do that here. And if you look in one of these grid squares, there's again these round structures. Still is the cell body contamination, but these elongated sausages are again the rod outer segments that we are interested in. So this is the SEM image from above. This is the FIB image coming from the shallow angle, and we were milling the lamella in this region here. So this is before lamella milling, and this is after. In the FIB, it is really only this very thin sheet, only this thin white line here with a thickness of about 150 nanometers in this case. And if you look in the SEM from above, then you have here the white line that you nicely see. This is a layer of protective platinum, actually. But biological material, as thin as it is, barely produces any contrast, but it would actually be in this region here. Yeah, and with that, we then go into a transmission electron microscope. Our preparation was absolutely not perfect. This lamella is cracked. That is also not how it should look like. And if you zoom in, this is an overview image at a bit higher magnification. You can already see this ordered membrane stack of the rod outer segment. But you can also see that these rod outer segments were damaged. Here the incisor was ripped open. Here the disc stack was distorted. This rod outer segment has a kink. So yes, the cryofixation can preserve your sample in a close to native state, but only in the state it had before you froze it actually, right? So our preparation is not really great. You should always keep that in mind, right? Okay. We always find anyway some areas where the disc stack looked intact, and this is where we acquired our tomograms. So here we have the respective tilt series, like we go through these images that we acquired at the different angles. And in my opinion, you already get a much better feeling how your sample is arranged in 3D. But the real magic happens when you do the 3D reconstruction. So now we are slicing through the tomogram. Every slice is just about 1 nanometer thick. And I find this just stunningly beautiful. So we have here the membranes, and you see all these blobsy densities in between them. And these are actually all the proteins involved in the signal transduction. And we can just see them within the cell. Yeah. Here comes the sad part. I told you about subtomogram averaging. Subtomogram averaging does not always work. You need rather large proteins with big structured domains, so they should be about 400 kilodalton in size or bigger, and it should also be a homogeneous system. This, unfortunately, is neither. These proteins are usually 80 kilodaltons in size, and there are all different types of proteins in here. I spent like 2 or 3 years of my PhD trying to average this and assign it to the proteins, and I failed, at least with the algorithms we had back in the day. So keep that in mind. Subtomogram averaging is amazing, can produce amazing results, but it's not always applicable, okay? So what can we do with this data? Well, the first thing that we did, we just measured the dimensions of the disk stack in a really unperturbed state. And it turns out that there are 2 features that seem to define the dimensions of the disk stack. And that is, on the one hand, the diameter of the disk rim, where a bilayered membrane is bent to a diameter of 24 nanometers. And that is actually extremely high in nature. and also the regular stacking of the disks, which is always in the order of 14 nanometers. Yeah, so we started with the stacking of the disks, and actually, based on conventional staining on simple 2D projections, people came up with a model already way back in the days, and they saw always these zipper-like structures here. And from this, they concluded that these membrane disks may be interconnected like the different layers in a parking garage, and that this may facilitate the spacing of the disks. And then we looked in our cryo-fixed samples. This is just a high-dose exposure, so not a tomographic slide. You see the contrast is much worse because we don't have the heavy metal staining like in this conventional fixation, but we also saw that there are some zipper-like structures. Also in our tomographic slices, everything is even more noisy, right? So the contrast is really not great, but still I think this looks for me absolutely like a zipper-like structure. But when we then continue in the tilt series, we actually see, oh, these membranes are not interconnected. This is actually the disk incisure. So what these people saw here, they just projected at the right angle through the disk incisure that it appears like it actually is a connection of the membranes. Not a big deal, but a very nice example that tomography can really be helpful in order to get reliable 3D data from your sample and not to be tricked by two-dimensional projections. What is much more likely to be involved in maintaining the disk stacking are actually molecular spacers or some sort of linker molecules. And I was a bit disappointed because John Heuser, he produced already so many good results in his life that he didn't even bother to show this data yesterday. But I was really impressed by the beauty of this data. So these are swollen rod outer segment disks, and the plasma membrane is removed, and we look onto them, and they saw all these little linker molecules between the disk rims, actually. So this was in 1982, basically 8 years before I was born. They already had beautiful data like this. Simply amazing for me. And we actually saw something very similar when we looked into our tomograms. So there are these linker molecules at the disk rim. It really looks sometimes the disks are stitched together like the beads on a string. This is close to the plasma membrane, but a similar thing we see when we are looking at the disk incisure. But also in the parallel membrane planes, we sometimes see some structures that seem to link the membranes together. And what we then did, we decided to segment them, to render them in 3D basically. And to do this, we created masks for the membranes here in yellow. And then we selected groups of voxels that connect these two masks together basically. Here we already sorted them in connectors that appeared close to the disk rim and the ones between the parallel membrane planes. And then we analyzed them statistically. So these connectors at the rim, they had much closer nearest neighbor distances, so they were much closer together. They also were much shorter and appeared at a lower gray value, which translate into a more dense structure. So we think we have two different types of connectors here. We also calculated their density per surface area, and then we crunched the literature. What do we know? What proteins are there? How abundant are they? How big are they? And based on this, we have a theory that the disk rim connectors might be GARP2, and these between the parallel membrane planes phosphodiesterase 6. But actually, just purely based on our tomographic data, we cannot really prove this. And that is another problem that cryo-electron tomography has these days. I really love this article that was published recently, and it's the caption below: cryo-electron tomography is a hugely promising tool in visual proteomics if researchers can work out what they are seeing. And in this case, we were unfortunately not. Yeah. So we probably have a bit more exciting results for the organization of the disk rim there. This is again just a simple high-dose exposure, so not a tomographic slice. And what you see there seem to be like 3 densities protruding into the disk lumen. And here we also did some tomogram averaging in order to understand how are these 3 rows of density organized in 3D. This is the average that we got. So here we have a slice through the average, and this is an isosurface representation. And for your orientation, here's the cytosol, the disc lumen, the inner leaflet, and the outer leaflet. And now we are looking on top of this, and it actually forms in 3D like a regular scaffold composed of 3 rows. So these rows form like a continuous belt around the entire disc rim, and they seem to have a certain repeat size. So this is row 1, row 2, row 3. And if we now look only at the central one, we see that we have nicely resolved transmembrane density or density blobs. There's also a repeat on the cytosol. And if we look again from the top from the lumen onto the scaffold, we actually see these 3 repeats, and they stretch out little arms in order to connect to the peripheral rows actually. Yes. And now it's a bit difficult. Now I want to show you gray value slices at different points from the cytosol to the disc lumen. And when I talk about the direction along the row, I mean this one here. So this is a slice in the cytosol. Here's again the direction along the row. And these are the repeats. So we have 2 little blobsy densities per repeat in the cytosol. They seem to diverge inside the transmembrane area, getting a bit closer the more we get into the disc lumen. And inside the disc lumen, they are actually in very close contact, but also the repeats within the row are also touching each other really here. And if we go further out into the disc lumen, these 2 densities are actually diverging again. This is when they form the arms to the peripheral rows. So the shape of these repeats actually reminds me of a tooth. So in this tooth-like analogy, the root of the tooth would be this diverging transmembrane domain with the small cytosolic part. Then we have this globular part in the disc lumen. It's like an assembly domain that keeps the whole scaffold together in the individual row. And in the head domain here, they form the arms to connect to the neighboring rows. We also did this analysis not only for the central, but also for the peripheral row. And it seems to have a fairly similar organization where we have these transmembrane densities, something on the cytosol, and also this globular assembly domain in the disc lumen. The average has a poorer quality, probably because the one in the center, this row, is fixed by its neighbors, but the one on the outside is more flexible. It can more wiggle around, and that's why the average itself has a worse quality than the central row. But there's one difference in the organization. If you look at it at a lower threshold, we actually see that in the peripheral rows, these repeats are actually linked by a strong density on the outside here. So we were again wondering, what is the scaffold made of? And here we were lucky that there are actually 2 complexes known that are really abundant, localized to the disc rim exclusively, with large disc luminal domains. And this is on the one hand the ABCA4 cassette transporter. It's known to be important for the long-term viability of the rod outer segment, and complexes composed of peripherin 2 and ROM1. And yeah, I mean, we already had good hints that peripherin ROM1 might be responsible, because if you isolate it and reconstitute it with membrane vesicles, it actually introduces some membrane curvature and forms these very interesting tubes of membrane. So we already had a good idea that peripherin ROM1 is a good candidate for the scaffold, but to be sure, we also size-wise, it actually fits very well. But to be sure, we also generated a subtomogram average of the disc rim in where we knocked out ABCA4, so we got rid of this in our rod outer segment. And the average is much worse, but I hope you can still agree that these structures look very similar, that we have these 3 interconnected rows of densities with a certain repeat size. And that is another thing what I love about cryo-electron tomography. The in vitro data told us, yes, this peripherin ROM1 may form some membrane curvature, but inside the reaction tube, it generated a diameter of almost 100 nanometers, and it was a continuous scaffold. And here it forms inside the cell with subtomogram averaging. We see that it actually induces a 24 nanometer curvature, and only with these 3 continuous rows, right? So cryo-electron tomography really shows us directly what proteins do inside the cell, and in the reaction tube, they quite often behave quite different. Good, that concludes this part. we introduced some methods to isolate rod outer segments. We measured them, found 2 types of different spacers there, even though we couldn't assign them. But the most important part is that we could basically characterize the scaffold at the disc rim there. Okay, coming to the second example, and this is how we use cryo-electron tomography to peek between moss cells. Yeah, actually we are now working on plasmodesmata, and these are membrane-lined channels connecting neighboring cells across the thick cell wall in plant cells. They're extremely important communication channels and are vital for plant development and growth, but we barely understand how they work, and they could help us to make plants more nutritious and more resilient against viruses. But we are not there yet. We just want to understand how they work in the first place. And what was done here was basically what we know of the morphology of these channels is based on plastic or conventional EM or ET methods. And the data that is out there in the literature is really bad to really understand how they work. So it's about time that we analyze them with cryo-electron tomography to see what is really happening there. And the system that we are using to look at this is the small moss Viscometrium patens, which you see here. And in the early stages of its life cycle, it forms linear chains of cells that have a diameter of about 25 micrometer. And plasmodesmata are only formed here in these junctions between the cells, or at this junction between cells. And initially, we tried exactly what we did before. We isolated the moss, we placed it on a grid, and plunge froze it. That is actually quite nice, because then these moss cells are exposed right on the grid. We can immediately identify our target area, which is the junction between cells, and then mill our lamella there. Unfortunately, 25 micrometer thick plant cells are way too fat to be vitrified by plunge freezing. And that becomes obvious when you look at this tilt series here. These storm cloud-like patterns are actually introduced by crystalline ice. And ice crystals grew, so they distorted our samples in a way we cannot anticipate. So this tilt series, or the data we will get from it, is actually corrupted, and we cannot trust it anymore. So at this point, we had to go to the high pressure freezing. And we started initially with the waffle method that Jürgen already talked about. What we do there, we take a grid, but now upside down, place it on one of these metal carriers, and fill our sample into the wells between the grid bars that have a height of 25 micrometers, so our moss cells fit in there perfectly. Then we close this with another metal carrier and do the high pressure freezing. The nice thing is, afterwards, we can recover our grid without those thick metal carriers around it. But unfortunately, Jürgen also mentioned it already, now our sample is buried inside a thick layer of vitreous ice. Do you see our moss here? No, right? And that is really the big problem that we have with these high pressure frozen samples. So what we then do, we load them into our Leica SP8, which is a cryo-confocal microscope equipped with a cryo stage. And we can use this to quickly screen all the grid squares on our grid and identify squares that are actually promising in that they have our target area, the junction between cells, somewhat in the center of the grid square. And then we can do the FIB milling again. Unfortunately, these samples are now much thicker, and we cannot mill just directly from this normal milling position that we talked about before. What we first usually do, we turn our sample around and dig holes around our target area, and we call them trenches. So now we turn around the stage, and now with the focused ion beam, we're actually shooting straight into our sample. The problem now, these confocal images I showed you before are not precise enough to really precisely target the junction between cells. And it will be really hard to find them just like this and not to miss them. But luckily, our microscopes have these integrated fluorescent microscopes. In our case, that was the Meteor produced by Delmic. And its optical axis is basically parallel to the FIB, but it's physically at a different position. So what we can do, we move our sample over, bring in the objective of the integrated fluorescent microscope, take the fluorescent microscope images, and then move back to the FIB. But that still doesn't help us. We need to somehow correlate the FIP and the fluorescent microscope images. And to do that, we navigate to a square we identified in the confocal, and then we simply mill a hole in there. Then we can find this hole in the fluorescent light microscopy images. From there, we measure the distance to our target area, the junction between cells, and then we use this information to define the pattern for the trench milling around our target area. So the trenches, these are the holes after we milled them, and we can still check in the integrated fluorescent microscope after trench milling, and our junction is still there, so perfect. Then we can go back to this normal milling direction, where we come with the FIP from the shallow angle. This is the front of the block that we just carved out with the trenches, and then we can mill a single lamella right here on the grid. But yeah, at this point, 2 more challenges that we had to tackle, because our cells have a thickness of about 25 microns. But our lamella is only like 300 nanometers thick or thinner, so we lose about 99% of the volume of our cell when we just mill a single lamella. So the throughput is rather low. And the other thing is, at least in our case, quite often we see that our cells are damaged. The swell is 25 microns high, so one layer of cells fits in there perfectly, but quite often we squeeze 2 or 3 layers in there, and then actually the cells get squeezed and totally messed up with this kind of preparation method. We fix the damage by going back to the classical high pressure freezing, because these wells have a height of about 100 to 300 micrometers, and in the process of freezing we are actually not damaging them. But now we are actually forced to literally lift out a piece of material and attach it to another grid, because we cannot mill right here in this carrier. Milling through this thick metal layer on the bottom would actually take us weeks, so we cannot really do that. Yeah, and for the lift out we of course first need to do the targeted trench milling as before. This was just here on this, the sample is frozen in this carrier here. We identified this junction and did the trench milling kind of as before. And then we go back to the normal milling direction. And we use this lift out system that Jürgen tackled before. So the lift out system that we have is the Easy Lift from Thermo Fisher, and it's literally just a small needle that is cooled, and we can precisely control its position, like really with nanometer precision. In the camera view, you barely see it in and out here, but in the SEM, it's actually quite clear that it's a thick needle. And yeah, then we go in, we use the redeposition milling to attach the block that we just carved out and lift out the entire block. I will only show you the double-sided attachment. So initially, this lift-out block is a bit wider than the distance between the vertical bars in these 400 by 100 mesh grids. We precisely adjust its size that it just fits in between the bars. Then we attach the lower part and slice the lower part off. And then we repeat this process until the entire lift-out block is basically sliced up. So in this case, we also get several lamellar precursors per our target areas, and this significantly improves the throughput that we have. Yeah, in the end, what I really like to do is, so we have these 5 precursors here, and I really like to go back to the integrated fluorescent microscope and try to check whether we were actually hitting our target area. And we can see in the first lamella, actually not. The junction between cells is only in lamella 2, 3, and 4. That already tells us we don't need to bother working with this one. And also the front is usually quite burned after the lift out, and it also contains no information here. So what we then do, we just create a new clean front and remove material that is actually not interesting for us. Yeah, then comes the fine milling. And here's just one example of a tilt series. You can see now with this workflow, it's actually storm cloud free. So this material was really vitreous with this approach. And this is one of the tomograms. I just find it really beautiful that we can do these things. We have a mitochondria here. This is the cell wall that we are actually interested in. And these are the channels, these plasmodesmata that we are targeting. And we can already see some densities that haven't been seen with conventional staining methods. And now we try to compare this to certain mutations where we know the transport through the channels is different. And we try to use this information to elucidate how these things are actually working. But today I really just wanted to show you actually our workflow to do this, and maybe it can be helpful for you in the future because we actually have all the equipment to do this. So yeah, for our plant cells, we couldn't use the simple cryo-electron tomography workflow. Plunge freezing doesn't work, so we used high pressure freezing, either with the waffle method or classically in the metal carriers. Then we used Leica cryoconfocal to screen our grids, and the integrated fluorescent microscope is really needed for us to do this precise trench milling around our target area. Depending on how we froze the cells or what we want to do, we can then either do the on-grid waffle milling, but today we actually really prefer the serial lift-out with double-sided attachment because it significantly improves the throughput, and these lamella are amazingly stable inside the microscope for data acquisition. Good. I hope you are not yet all asleep. There's one last thing that maybe you're really curious what I'm doing here with so many accomplished scientists and really experienced electron microscopists. The reason is I had the great pleasure to train Carol back in Germany how we do cryo-electron tomography. That's her on our last day, actually. Behind us, this is the Aquilus 2, where she probably spent most of her time in Germany. Yeah, we didn't force her, right? And it was really amazing. So Jürgen's philosophy is you can learn cryo-ET on whatever sample, like some arbitrary yeast or HeLa cells, but you learn best if you work on your own system. So Carol poured Paratrypanosoma confusum, which is basically a non-infectious ancestor of the cells you're otherwise working with, right? And it was the only non-infectious organism she could smuggle into Germany without being punished. And we let them recover for 2 days after she came to Germany, and without thinking a lot, we put them on a grid, did 1 hour of plunge freezing, then we took over half a day of FIP milling. The lamella looked like crap. They were heavily contaminated. When we loaded them into the cryos, most of them actually cracked, so they barely survived the transfer into the microscope. So we acquired for 1 day data, and probably these are amongst the most beautiful tomograms I've ever seen. I will actually show you just this one example, because Carol has a talk on Friday, and I always adore how beautiful nature is, but she may actually be able to explain you what we are seeing here. And yeah, there are so many structures that were interesting to us that we just started to do some initial subtomogram averaging. Jürgen told about it. Everyone does ribosomes, like these machines that are translating mRNA into the polypeptide chain that folds into a protein. This is very blobby, like really serious blobology here. For those who don't know, blobology was the nickname for electron microscopy and structural biology in the early days because it only produced this very low resolution structures of a few nanometers in resolution, while X-ray crystallography already achieved atomic resolution. And compared to that, electron microscopy looked blobby. That's why blobology, and this is blobology. But even at this resolution, you may dock in a high resolution structure of a close or of a relative or closely related organism, and you may find missing or additional densities, and this may hint on some interesting story. We also did microtubules, the next lowest hanging fruit, and these guys always have 13 protofilaments, and this is what you quite often see inside cells. But if you isolate tubulin and you let it polymerize in a reaction tube, it often forms 14 protofilaments. And so it's another example that in the cell, things quite often behave different than if you would purify them and reconstitute them. So yeah, that is actually not really interesting, even though these microtubules are filled with some additional densities. That might be also something that people could be interesting in the future. But what was really striking and new to us are the two following things. So what you see here, these filaments actually, they are in the extracellular space around the flagellar pocket. And when you look in classically fixed cells, there is no structure density there, so somehow these conventional fixation protocols totally destroy the structure. And this is also, again, just some very blobby initial average of what we have there. It has a certain repeat size of about 9 nanometers, and we have no idea what it is yet, I think, right? But this is totally something that that you will probably go for in the future. And also, Carol immediately spotted it. If we slice through this tomogram again, if you look here, this is the contractile vacuole, and there seems to be these loopy densities on the surface of it. And we just have 800 subvolumes here that are horribly oversampled, but we can already see that there seems to be a continuous scaffold that might be involved in shaping this membrane structure there. Really just some serious blobology, but I think the subtomogram averages already give you a much better feeling of what's going on inside the cell. Yeah, but it also nicely illustrates the problem that we talked about before. Oh, I deleted it because we have still no idea what we are looking at here, and this is really a difficult thing to figure out. But yeah, stay tuned what is coming from Wanderley's lab in the future, because you guys have all the equipment to do that here, and I'm also really curious. Yeah, with that, I'm at the end. I have to thank many people for this, especially Wolfgang Baumeister and Jürgen Plitzko for providing us this amazing high-tech playground to do all these experiments. And especially Jürgen's people, because we in the Baumeister group, we don't do methods development at the moment. We just applied the methods that Jürgen's people developed to our moss cells at the moment. So Christoph developed the waffle freezing method, and all of them together the serial lift out, which is extremely crucial for us. Anna and Christina, our CLEM experts, they showed us how to do all the correlative work to find our target areas. We have amazing support for the electron microscopes, and all the data acquisition is only half the work. Afterwards, you need to do something with the data, which takes the other half of the work, and we have also great support when it's about the data processing. Yeah, Julia Mohammed, Chris Palczewski, and Sanai Imanishi were working with me on the rod outer segments, and these are my colleagues with whom we are working on the MOS project. Thank you for your attention.
Well, thanks, Matti, for the wonderful talk. We have time for some questions.
Thank you for the beautiful talk, and I'm very grateful that you have shown us that not everything works as we for the first time, and you have to try and pick up what's good in the sample. But what I've compared the photoreceptors of the cells, the cones and the rods out to the thylakoids of the chloroplasts. And I wonder, they both react to light in a sense. And those structures you have seen in the curves, they are responsible for the shaping, and many questions arose to me. You do not have to answer to know that.
I'm happy to answer all of them.
Okay, and how does the cell forms? What's the generation of those so regular membrane systems? And if you had ever thought on comparing those discs to the thylakoids?
Actually, we do have chloroplast tomograms, but I never checked the rim. I think the rim has a different architecture in thylakoids. I think they don't have this 24 nanometer bubble on the top, but I can look into it actually. And about the formation of the thylakoids, I have no idea actually, so I cannot compare. But the rod outer segment is actually a modified primary cilium. And I think usually what they do, they would shed lots of membrane vesicles. But the peripherin 2, which is one that we expect forms this high curvature, the disc rim, has on its C terminus a signal that prevents this shedding, so all these vesicles are retained, and this is then the material that forms these membrane discs. apparently, or this is the hypothesis that people have at the moment. But apart from that, I don't know. It's also really hard to study. If you knock one of these components out, the rod outer segment doesn't form, and then you cannot compare how it works or doesn't work in the absence of a certain protein or mutation. But yeah, this is what people think, and we also think that these spacers have, they are at least involved in organizing and maintaining this architecture with the precise distances between the disks. We can talk about this more, but also my knowledge is a bit. And I mean, this is something I couldn't squeeze into the talk itself. We have lots of electron microscopy experts, Jürgen, Grant Jensen, they all did lots of subtomogram averaging and cryo-ET because certain things are really difficult to tackle, and you should bug them what is possible and what is not possible as long as they are here, I feel, yeah. And if I can just go over this real quick, I mean, you have all these capabilities of doing the serial lift out, you have integrated fluorescent light microscopes and this needle in your FIB, but if you can go for easy, go for easy. Don't do the fancy thing with the lift out. If you can work simple with plunge freezing, if you can use this to address the question, go for this. It will make your life easier, it will be much faster, you will have a higher success rate. And I think Paratrypanosoma confusum nicely shows you should invest some time to find a model system that behaves well, that is easily accessible in cryo work. Someone is working on infected retina, you can do high pressure freezing of the retina and do the lift out on high pressure frozen retina to see what's happening in the cell. It's possible, but it will be painful and hard, especially if you start. If you find an easier model system to work out the interactions between host and pathogen, go for that first. And with the subtomogram averaging, we talked it doesn't work, you need, doesn't always work, you need rather a large complex. You must be able to pick it easily in your data. It should be like 400 kilodaltons, the structured part of it. And if you see it in in every other tomogram once, you will need to acquire 10,000s of tomograms for a high resolution structure, and this is probably very likely to not work. So keep that in mind. You can waste entire PhDs or entire lifetimes on projects if they are not designed properly. Don't get into that loop of wasting your time on a project that doesn't work.
But yes, in relation to your data on the plant cells, I got the impression that the ER in some way connects to the plasmodesmata. Am I correct?
Yes. So actually, I didn't talk so much about the biology, sorry for that, but actually there's a tube of ER going through these channels.
Across
the
channel?
So across plasmodesmata, the plasma membrane is continuous, the cytosol is continuous, and the ER is continuous. There are huge domains inside plants where you cannot distinguish one cell from the neighbor, so they are not a blob of isolated cells, but this is really a supracellular organism, and that was blowing my mind when I started working on this.
Okay.
Thank you for this wonderful talk. I would like to ask you, could you talk a little bit about contrast inside the microscope? What kind of plate you use, and what is expected for the near future? For example, resonant cavities, etc. For the generation of contrast, especially in low magnification, because you solve this problem by using fluorescence to find small regions to analyze in the electron microscope. But I'm asking about contrast inside the microscope.
You mean SEM contrast?
Yes, transmission microscope contrast, the observation of frozen lamella. How do you can improve contrast? If you use, for example, Volta plate or something.
Actually, the rod outer segment tomograms I showed you initially, they were acquired with the face plates, and this can significantly boost the contrast of your raw data. What I didn't talk about now, that neural networks are transforming also our life in cryo-electron tomography, and actually CryoCare is a network that is specifically designed to denoise our tomograms. And it's not exactly faceplate-like contrast if you acquire the defocus, but it's getting there. And the faceplate, it is amazing, but if you are not Radostin Danev who invented it, you will have a hard time to aligning it. Also, the phase shift is not stable, and when the phase shift develops too far, your data quality deteriorates again. And also for subtomogram averaging, it seems not, at the moment with the algorithms that we have, too beneficial for subtomogram averaging. So with conventional data acquisition, you seem to get better results at the moment. So therefore, most people in the field now try to avoid the faceplate if they can. And with this denoising methods, you can really get, even if you only acquire the defocus, get quite a good contrast. So maybe the plant tomograms that I showed you, they were actually only acquired with a rather high defocus, and this is after denoising. I think you can still beautifully see certain structures, ribosomes that form polysomes. You see all the densities inside the mitochondria. I think this can work for a good analysis.
So this is without plate. This is a software. Okay.
Any more questions? Okay, so thanks, Matthias, again. So now we will have the coffee break. That will be in the barbecue area. So you can just follow people to there. And we are back in 20 minutes, okay? Do you want to check now, or we can check it after the coffee break? We can check it now. Okay. Very good.
Thank you. I lost it in between a bit.
Let's continue. Please call everybody to come back, please. Perdão.
Hello.
É porque eu falei, let's come back, people. Eu falei,
Se tiver muito baixo, pode ser que seja muito baixo.
acho que não. Let's begin, people. Estão ouvindo, não?
Não está ouvindo? Fala de novo.
Falei. Será que é isso que o Fábio estava reclamando? Eu estou falando baixo aqui, né?
Let's begin.
Tá sim, tá saindo, tá? It's fine, the microphone. Deixa eu sair aqui de perto da caixa eletrônica, da caixa de som. Chega um pouquinho para lá. Hello, let's continue the conference. I have the pleasure to introduce Dr. Chang. He is Associate Director of the Institute of Structural Biology of the Perelman School of Medicine at the University of Pennsylvania, and Assistant Professor there of Biochemistry and Biophysics. In 24, he began his education studying mechanical engineering at Tsinghua University in Taiwan. I don't know if I pronounced it correctly. 2010, he did his PhD in structural biology and bioinformatics at the Academia Sinica National Tsinghua University in Taiwan also, where he performed X-ray crystallography, resolving several atomic protein structures. Then he started to explore cryo-electron tomography or electron cryotomography for studying macromolecular structures. In 2014, he studied cellular structure biology at Caltech as a postdoc, and then he got a position at Pennsylvania University, where he developed the first method of correlative cryo-electronic tomography and cryogenic super-resolution microscopy to locate structures in cells and established high-throughput cryo-ET data collection and subtomogram averaging methods to study structures in cells with high speed and resolution. Oh, yes? No. Okay. He has worked on cryo-ET for more than 13 years, and he has an independent group at Pennsylvania University, as I said, and produced and analyzed over 8,000 tomograms to unravel the structure and mechanism of several important molecular machines in tactile microbial cells. He is supported by the Beckman Foundation to establish the combination of super-resolution cryoconfocal microscopy and fluorescence-guided volumetric cryofocusing ion beam scanning electron microscopy with cryo-ET to enable the imaging of previous intractable targets. Dr. Chen has contributed so much in the area of structures and mechanism of the ROP3 secretion system in apicomplexan, like toxoplasma that he will show to us today, by cryo-ET, but he also works on the architecture and mechanism of the bacterial type 4 plus machines for motility and host invasion. You have several works on also in bacteria. So we have this great pleasure. Please, Dr. Chen. Thank you.
Thank you. Should I turn off this one? Great. Carol? Okay.
Oh, sorry.
Thank you. Thank you so much for the kind introduction, and thank you so much, Wanderlei, for the invitation for me to come here and share our work. As introduced, my lab is in the city of Philadelphia in the States, United States. And in the past 4 years, my lab has been using cryo-ET to study in situ structural biology of parasites. Okay, so the particular type of parasites, epicomplexan parasites, which is a big group of single-cell organisms comprised of more than 5,000 different species, including some of the well-known human pathogens like Plasmodium, transmitted by mosquito, cause malaria, kill 500,000 people around the world every year. Toxoplasma gondii, I know several of researchers here studies, which can come transmit through cat, and then when they come to our body, literally they can invade any type of cell in our body and can transmit from mother to fetus and cause congenital diseases, a lot of health complications. Cryptosporidium transmit from the feces of livestock like cows. If we drink those contaminated water, it will infect our intestine tissue and cause very severe diarrhea, and actually is one of the leading cause of waterborne disease around the world, causing severe burden of health of particularly young children. So although they have many different life cycles and then they come to our body in different ways, but the same thing is that when they come close to our cell, they will use their defined cell apical end to sneak into our cell like this way, like open a portal and then dive in and close, and then live inside a vacuole made by the membrane of our own cell and hiding inside and propagate in the end once they reach a certain number, they will lyse the host cell and come out and ready to find the next host to invade. Okay, so this repeated cycle of the host cell and is a major contribution of the symptom. For example, in malaria, this is our red blood cell. Okay, and this is known that for this invasion to happen, a specialized membrane-bound organelle called rhabdoid need to secrete its content directly into the host cell. And some of the proteins will then come back to the surface of the host, expose out, and then some other proteins on the surface of the parasite will then grab onto those anchors they put into the host. And this interaction will create a tight junction like a ring surrounding this parasite cell. Inside the parasite, there are ectomyosin motors can move this ring from the tip to the base of the parasite. And this is how they wrap themselves by the host membrane and create this vacuole as their niche inside the host. Some other rhabdoid protein will then decorate the surface of this vacuole, further defend this parasite from the host immune mechanism. Other proteins even go down into the host, alter the gene expression profile of the host, further help the parasitism of this single-cell organism. So as you can see, the secretion of rhabdoid into the host is very, very critical for this parasite to invade the host and become a successful parasite. However, nothing was known how this rhabdoid content is secreted through 3 layers of membrane. The rhabdoid membrane, because this is a membrane-bound organelle, and also the parasite membrane, and then the host membrane, so 3 layers of membrane. How this secretion mechanism is controlled is unknown, and people only know this controlled secretion of organelle from one cell directly into another cell is pretty unique in cell biology. So this has been called kiss and spit. So, but the mechanism of how they kiss and spit was unknown at molecular level. Traditional thin section EM has looked at this parasite, in this case is Toxoplasma gondii. They were able to show those are the elongated structure of rhabdoid, contains a thin neck pointing to the tip of the parasite, and also a bigger bulb loaded with proteins. However, the resolution of traditional EM cannot show how the structure of the rhabdoid was maintained, and of course, what kind of molecular machines are there govern the secretion of rhabdoid into the host. Okay, and also there are interesting differences in terms of numbers of rhabdoid per cell in different organisms. In Plasmodium, the parasite caused malaria, it's known that they always contain a pair of rhabdoids. Okay, but in Cryptosporidium, the parasite caused diarrheal disease, only contain 1. Okay, and Toxoplasma gondii, on the other hand, can contain more than 10 rhabdoids per cell. So how different type of organism coordinate the secretion of different number of rhabdoid into the host is also pretty much unknown. So we set out to understand those questions by applying cryo-ET to look at these parasites at higher resolution in 3D. So we first took a Cryptosporidium, which contains only 1 single rhabdoid per cell. We froze them on cryo-EM grids by plunge freezing. Those are individual Cryptosporidium cells. And then we can focus on their tip region and take high-resolution projection image. As Matthias showed before, we can turn the sample degree by degree, take this tier series, and this allows us to computationally calculate the 3-dimensional tomogram of this part of the parasite. So slice by slice, right away, we see extremely rich structural features across this tip of the parasite. If we segment different components in 3D with different colors, right away we see this amazing big structure. Okay, at the tip is a structure like a cage. The name is conoid. It's largely made by tubulin proteins, become the highly curved arcs. And then this is another ring showing purple here. It's like a microtubule organization center, sending out microtubules spreading into the cell body. So the entire thing acts like a cage, defines the apical area of this parasite. And within this cage, it houses several different types of secretory organelles, showing yellow and orange here. And today, we're going to focus on this orange one. This is a single rhabdoid inside this Cryptosporidium parasite. Okay, the first thing we did is to look at the tip of the rupture and see, okay, how does the tip of rupture connect to the plasma membrane of the parasite? So in every image, in every tomogram we saw looked, there's always a beautiful ensemble of molecules at the tip of the rupture. Okay, this is a cross section of the tomogram, and this is the rupture. And then at the tip of rupture, we always saw a membrane vesicle, okay, at the tip of rupture, and followed by some proteinaceous density, and then dark on the plasma membrane of the parasite, okay, because the vesicle is on the apical end of this parasite, so this is called apical vesicle, AV, okay. If we look closer to the AV, so this is the AV, we can see those proteins even reaching down to the AV and reaching up to the plasma membrane of the parasite. Okay. In tomograms, we can cut through in different slices. In this sample, we can cut through this slice and turn it 90 degrees and see the top-down view of this blue density. And what we saw is very beautiful. It's a flower-like structure with 8 clear petals. So we are super excited because this is something new. We never found it before. So in order to improve the resolution, we've followed by subtomogram averaging. Basically, we take several hundreds of tomograms of different cryptosporidian cells. In each tomogram, we found this single apical vesicle. Okay, this is a plasma membrane apical vesicle, tip of a rupture. These are 10 examples out of few hundreds of examples. Okay, and they are easy to find because each one of them look like a smiley face. so it's very cool to find them in the cell. And in computer, we can superimpose all those smiley faces, and we feel very happy doing those, as you can see. And then after subtomogram averaging, we can get an even better smiley face. In 3D now. So we can go through different slices of the subtomogram averaging, and right away we found, wow, they are intricate molecular densities in between the apical vesicle and the plasma membrane of the parasite. Okay, and if we go from the different direction, from the top-down view, we can see this beautiful flower-like density that we're reaching down and clamping this apical vesicle and tethers it to the plasma membrane. So this is a very intricate multi-component machine which is there at the tip of a rupture. Okay. And after we segment different pieces of density with different color, the next thing we can do is to hide different components and then study their interconnectivity in this molecular machine. So we saw these different anchors are linking one to another all the way to some protein densities in the plasma membrane of the parasite. Okay, we even found there's a big barrel-like structure inside the AV, and there's another barrel in front of AV, followed by a cogwheel-like structure as a tentative gate, gating a channel inside the plasma membrane of the parasite. Okay, and because of the location of this big molecular machine and some other data I will show later in the talk, we decided to name this machine Rupture Secretory Apparatus, RSA. Okay, and if we turn the RSA to another angle and look from outside of the cell, the RSA look like a rosette of 8 densities surrounding a central channel, and this is likely where the parasite kiss the host and spit their content of rupture. Okay. So, and this provides the first structural framework for us to start understand the mechanism of how rupture is secreting their content into the host. Okay, so this is a cross section of the RSA, this is the plasma membrane of parasite, this is AV and rupture. So we can start to think, okay, in order to make a channel for the rupture content to go out, very likely this molecular machine will conduct some conformational change and pinch these 2 membranes together and create a passageway and deliver rupture contents through them. But this is not the entire story because there's another membrane this content needs to go through, which is the host membrane. So most likely not only this machine can pinch these 2 membranes together, but other components likely can further breach the host membrane and form a very stable passageway to deliver the content. And this is under active investigation in my lab right now. Okay. But in the same time, we also are curious, how about Plasmodium, the parasite causing malaria? It's known to have 2 ruptures per cell, but no one knows if there's an AV of course, no one knows if there's an RSA. Okay, so we took some tomograms of this parasite again, and then sure enough, we were able to find an apical vesicle and dock with some RSA proteinaceous density in front of the parasite plasma membrane. Okay, the AV in this parasite look more empty and also variable in size and shape across different cells we imaged. But very interestingly, in every cell we imaged, we see this AV can coordinate the tips of both rupture. Okay. And more interestingly, we actually collected tomograms of more than 200 cells. In about 2/3 of the cells we imaged, they do have two ruptures, okay, and their tip docked to an AV and followed by an RSA, okay, depicted like here in 3D. But in a subset of cell we imaged, we saw there's actually no AV, okay, instead it's the tip of one of the two ruptures directly docked to the RSA density. And when we saw that, the tip of another rupture drop it down and then start to wrap around the neck of the docked rupture. The most amazing subset of the data is that in this subset, we saw there's also no AV, and also the two ruptures have fused and using their common tip docked to the RSA. Okay, so seeing this, we're super excited because when people use traditional thin section EM to study Plasmodium infecting red blood cell, this phenomenon of fusion of two ruptures has been seen and has been concluded as an activity for rupture secretion. So we think we were very lucky somehow during our simple preparation for freezing for cryo-ET, although there's no red blood cell around, somehow this process have triggered the beginning of rupture secretion. And so that's why we have some subset of the cell having this fusion activity. So the next thing we did is to conduct subtomogram averaging of this part of the structure separately among these three classes, and hoping that we can see some structural difference of the RSA corresponding to different stages of rupture fusion. And the answer is yes, we did. So this is the subtomogram averaging of the side view of the plasma membrane of parasite, the RSA, and this is the top part of the AV, okay? And then in this case, when there's no AV, we saw this is the tip of the rupture docked into the RSA. The rupture is filled with protein, so the density is higher compared to the empty AV. But other than that difference, the structure of the RSA looks pretty similar to one another. But the interesting thing is this one, when the two ruptures fused, we saw this gate density inside this RSA disappeared, suggesting a channel has really opened for content to go through. And also the density inside the rupture tip become lighter compared to this one. And this open up of a passageway can further be appreciated if we look at the cross-section of this slice and turn 90 degrees, look from the top-down view, and you can see the channel in the center does look lighter compared to these two stages. Another interesting thing we saw by comparing these three structures is that when we look at the surface of the structure from the top-down view, this is the rosette of the RSA in Plasmodium. It contains two rows of A densities, outer row and inner row. In this conformation, the inner A dots have disappeared. Okay, so if we do a three-dimensional morphing of this density from this one to that one back and forth, we can start to see how the gate is opening up. In the same time, different regions of the RSA is interacting with the plasma membrane of the parasite, likely causing the structural difference of where the kiss and spit the content to the host. Okay, so resolving this conformational difference of the RSA corresponding to different morphological changes of rupture fusion further suggests this is indeed a molecular machine governs the secretion of rupture. Okay. And furthermore, this study allows us to, for the first time, understand the potential role of the AV, which might be a trigger, okay, staying there to prevent rupture secretion prematurely. But somehow, if there's a signal for the rupture secretions to start, very likely the AV will first fuse with one of the tips of the ruptures. And that somehow will further trigger the fusion of the rupture and then allow the secretion to happen. Why they want to do that, we don't know, but this is really suggestive to me that this is like the compound glue. You know, there's a type of glue. You have A and B. If you use them only, A or B, they will not work. You need to mix them together. They become very sticky, and then you can really do the job. So one hypothesis is that this two rupture actually contains different type of proteins. They need to mix together and somehow make things happen. Okay, but this is pure hypothesis, remain to be proven. Okay. Okay. So how about Toxoplasma gondii? And this is a parasite that can invade any type of cell in our body, contains more than 10 ruptures per cell. Do they have a very big AV coordinated secretion of 10 ruptures or different ways? Okay, so we took tomograms again on this type of parasite, and this is a tomogram of one of the parasite, and right away you can see amazing complexity of the tip of these parasites. Again, we see this beautiful cage-like structure made by tubulins surrounding a lot of secretory organelles inside, define the apical end of this parasite. Okay, we imaged again hundreds of cells of these parasites. We look very thoroughly into their apical end, try to find these 10 or more ruptures. But in every cell we look into, we only found 2 ruptures inside the conoid. And these 2 tips are docked to one single AV at the tip of the parasite, just like what we saw in Plasmodium. Okay, by conducting a subtomogram averaging of this component, we again resolve a very similar looking RSA, clamping this AV at the tip of the parasite, have a very similar looking of rosette, like our other 2 species, and suggesting this is indeed a conserved molecular machine govern rupture secretion in this family of epicomplexan parasite. Okay. So we're interested, okay, how about other ruptures? There are around 10 ruptures. Where are they? Okay, so this is one tomogram. Okay, we imaged further down into the cell body, and this is the tip of the parasite. This is the AV. Those are the 2 ruptures docked to the AV. Lower below inside the cell, indeed, we can find the tip of other additional ruptures. And we can look at their tip, and we can blow them up. Okay, so the tip of those additional ruptures looks actually identical to the ones already docked to the AV. They have something at the tip outside of the rupture and an empty space inside the lumen at the tip of the rupture. Okay, and also the membrane is lined with these dashed lines like this one. Okay, those dashed lines are very interesting because in 3D, if we cut through the center slice of the rupture, they look like dashed line next to the membrane. But if we go to the top or bottom slice of this rupture, they look like striations with different angles. So in 3D, they're actually right-handed helix lining the membrane of the neck region of the rupture. And because the neck is so rigid in terms of the width, so we were able to crop out overlapping boxes along the rupture neck, conduct subtomogram averaging, and we were able to improve the resolution from this to that. Okay, so in fact, each striation contains 2 parallel lines, and each of the strand have a clear density directly insert into the membrane from the side view. So in fact, this is a double-stranded right-handed membrane-bound helix shaping the neck of the rupture. Okay, and likely is the factor producing the tip of the rupture and make them ready to associate with the AV. And because this tip and that tip look so similar, so we hypothesize that the tip, these additional ruptures, they are as ready as those ones stuck to the AV ready for secretion, but just don't get their turn to go to the tip of the parasite to secrete. Okay. So, and also very interestingly, in Toxoplasma gondii, there's always 2 microtubules inside the conoid pointing directly to the AV. Okay, if we go to different slices of the same tomogram, okay, we can see there's always a chain of membrane vesicles lining next to one of the 2 microtubules. Okay, if we look closer, we can see densities actually linking those vesicles onto the microtubule. So because of that, we call them microtubule associated vesicles, MV. Okay, and also very interestingly, in our tomograms, okay, sometime we saw the tip of those additional ruptures. Instead of interacting with the AV, they show tentative interaction with those MVs, which suggests both the MV and AV have the property of interacting with the tip of ruptures. If we do a side-by-side comparison of the AV and MV, they show very similar looking size and shape and content, even the coating of proteins outside. Okay, so all this let us wonder, maybe MV and AV are the same thing. They are just in different stages of conducting biological function. Okay, so we look back into our hundreds of tomograms of toxoplasma, and these are 6 examples. Okay, we found although the microtubule, colored purple here, can have different length among different cells, and also the number of MV can be different among different cells, but they all show tendency of packing to the front of the microtubule. Okay, suggesting there might be an active transporting mechanism putting them forward and jammed in front. Okay, and together with other data, we come up with this working model. Okay, so this is actually might be how toxoplasma is coordinating the secretion of more than 2 ruptures. Okay, we think in the beginning, the AV can only coordinate the secretion of the pair of rupture already docked to the AV, just like the one in Plasmodium. And once the secretion happens, the AV will be consumed. And when that happens, the first MV will move forward and become the new AV, form the new RSA, and that can coordinate the secretion of another pair of rupture. Okay, in the same time, other MV will continue to move forward. So this is a very, very cool AV reloading mechanism to fire ruptures like a machine gun. Okay, and this is actually matched to the phenotype of biology people found out before about Toxoplasma gondii. John Bustroy's lab in Stanford have showed many years ago Toxoplasma can actually secrete rupture content into multiple host cells before they commit invasion into one of them. Okay, and this activity has been proposed to be beneficial for them to succeed in tissue context when they are infecting animals. Okay, and so we are thinking this is the molecular mechanism how toxo conduct this sequential secretion of ruptures. So they don't want to secrete all 10 at a time. They want to do it sequentially so they can be more successful, affecting more cells. Okay. And while we are using cryo-ET to study the apical area of Toxoplasma gondii resolving the AV, the microtubule MV, and also the ruptures, my collaborator Dominic Soldati lab in Geneva, they have been using expansion microscopy to study the same region of Toxoplasma gondii. Basically, you chemically fix the cell, digest the protein, separate them out, infuse the cell with hydrogels, and then you can add water, expand everything, allow you to look at the sample by light microscopy with better spatial resolution. And this is their result. So they have do immunofluorescence labeling using antibody to tubulins. And this is what they saw. This is the wall of the conoid, okay, which is depicted here in cryo-ET. And these are the individual microtubules spreading out from the organization center, showing below. And this line is these 2 microtubules. So they were able to use light microscopy to see these 2 microtubules specifically. And furthermore, they have identified the protein specifically only bind to these 2 microtubules, but not other microtubules in the cell. And they were able to design a construct which knocked down these proteins before sample preparation. And there we were able to use cryo-ET to show once you remove that particular protein, these 2 microtubules are really disrupted. As a consequence, those MVs originally lining next to the microtubules, now it's everywhere. Okay, supporting that, those microtubules are actually acting as a track to organizing those MVs. Okay, and by using this construct, they repeat the assay John Bustroy did. They found the capability of toxo to inject ruptures into multiple host cells indeed is largely disrupted. And furthermore, in our tomogram, in this one in particular, we found there's actually one of the MV accidentally moved forward and docked to the plasma membrane. If we look from the top-down view in our tomogram, interestingly, we found 2 of the RSAs are formed, which is further support that those MVs are indeed precursor of AV. They were lined on the microtubules to prevent premature docking to the plasma membrane. Now, once we disrupt these microtubules, now this one got a chance to prematurely dock to the plasma membrane, create the RSA. Further support, they are indeed the precursor of AV. Okay. So at this point, we were able to apply cryo-ET to discover this cool molecular machine at the tip of these 3 model epicomplexan parasites. They all show very similar looking flower, suggesting a conserved molecular machine for rupture secretion. But also they have different interesting adaptations, like something in the channel, different size and shape of the AV, and also add-ons of microtubules and vesicles for different activities of rupture secretion. However, without knowing what proteins are making these machines, it's really a challenge of understanding their mechanism. So my collaborator, Maurice Lebrun and Aaron Turkiewicz, Maurice is in France and Aaron is in Chicago, they look into the tree, phylogenetic tree, okay? So here's us, okay, and those are fungi and then plants, and here is the epicomplexan parasite. So this parasite are in a superphylum called Alveolata. Okay, inside the Alveolata superphylum, there are 2 other families of single-cell organisms, ciliates and dinoflagellates. Okay, the same thing among them is that they all contain membrane-bound secretory organelles. So rupture is the one in epicomplexa, but in cilia, they have different type of membrane-bound secretory organelles. Okay, so cilia are single-cell organisms. They do not like to invade. They just like to chill in solution and swim by a lot of cilia. But people found many, many years ago, upon stimulation, they can shoot out tons of protein crystals in paramecium. They call trichosis. Okay, it's likely for their self-defense when there's a predator. Okay. Traditional thin section EM have shown this is a side view of the trichosis. They are covered by a membrane, so it's a membrane-bound organelle. And then people have tried to understand what's the structure governing their discharge, okay, by using a wonderful method. Back to John, freeze fracture replica EM, okay. Basically, they slam freeze entire cell in ice, and then they crack open the ice and expose these transmembrane proteins in between the lipid bilayer, rain down platinum and carbon to create a replica, wash away the cellular material, use TEM to look at this replica. And this is what people found. And many, many years ago, they saw rows of those features on the surface of cilia. Okay, if we look closer, there are 8 dots surrounding a center dot. So this rosette looks awfully similar to the RSA structure we saw in our tomograms. So Maurice repeated this freeze fracture replica EM at the tip of Toxoplasma gondii. And sure enough, she saw this similar looking structure where people saw by freeze fracture replica EM on cilia surface. Okay, so they are very likely similar molecular machine. And very luckily, in the cilia field, over years of study, people already identified genes, which once you remove them, the trichosis no longer secrete, and they are actually involved in the formation of that rosette in the cilia field. And those genes called non-discharge gene. And through in-depth genetic comparison and mining, Maurice and Aaron, they were able to find the relevant genes conserved in epicomplexan parasites. Okay, and by knocking out, like ND9 is one of the ND gene, ND6 is another one, Maurice indeed showed that invasion of toxoplasma into the whole cell is largely disrupted. Okay, and we were able to take the same sample, conduct cryo-ET. In wild type, this is the side view of the AV, docked tightly to the plasma membrane through the RSA structure from the side view and top view. And once we conditionally degrade one of the ND9 proteins, we start to see this attachment of AV being disrupted, and the structure of RSA is being disrupted. And now this really allows us to start to identify what proteins are making this core machinery. Okay. And this study led to this amazing understanding that in the epicomplexum superphylum, the same rosette, the same type of molecular machine, it was used in cilia to control the secretion of trichosis, and most likely just by fusing the plasma membrane and the trichosis membrane and release the protein crystal out. But somehow during evolution, epicomplexum parasite adapt another membrane vesicle, and that somehow allowed them to not only secrete content of this membrane-bound organelle into the environment, but also across another membrane into the host to allow them to really predate another eukaryotic cell. Okay. So now this is where we are at starting this particular molecular machine. This is a summary. This is a tip of this parasite. This is a host. Now we're able to discover there's a big molecular machine with the AV at the tip of the rod tree. We're able to start to identify different proteins involved in this machinery. In fact, there's already more than 15 proteins identified, likely forming this molecular machine. And we are now in the process of imaging individual mutants which lacking particular protein, so we can compare the structure with the wild type to dissect a molecular composition, the structural composition of this molecular machine. Okay, and of course, the holy grail is to look at this molecular machine in the act of secreting contents into the host. And so, like Matthias beautifully showed and Jorgen beautifully showed, this fit milling method is the method of choice we are now using to tackle this challenge. So we have been growing human cells on EM grid and then use fluorescently labeled parasite, infect them on the EM grid, and you can freeze them at different stages of rupture secretion and invasion, so we can do targeted film milling and to cryo-ET to understand how the molecular machine is creating this channel for secretion. So I will not go too deeper into this, but another big thing in this parasitology infection field is that not only this parasite infect individual host cells, but over time the chronic infection of parasite, particularly in Toxoplasma gondii, will have this thing called cyst, okay, which is a big vacuole, contains from 50 to even 5,000 cells inside the tissue. And very often they are in skeletal muscle, myocardiums, brain or eyes, which cause the biggest problem for chronic infection. Okay, so this is very much unknown in terms of their structural and mechanism there. And this is a MRI scan of a brain. Okay, those lesions are likely caused by chronic infection of Toxoplasma gondii. So we want to see, okay, if we can use cryo-ET to study this type of tissue infection context, especially in brain. So we've been trying to create a workflow which allows us to do cryo-ET on fresh brain tissues directly from autopsy. Okay, so I really agree Matthias' comment at the end. If we can go easy, we should go easy. If we can avoid high pressure freezing and leave out, let's try it first. So the first thing we try is to create a workflow without using high pressure freezing, but leave out, but study tissue sample of brain. So my student was on call. So in our school, there's a hospital, and also when there is a person died, my student will right away go there, run there to the autopsy room, and take a piece of the human brain, and then run back to the lab, because you know the fact is that once a person died, the brain tissue degrades very fast because of hypoxia. So we want to create a workflow which can, as quick as possible, to freeze the sample, allow cryo-ET imaging. So then my student can cut into a small section visually into about a 3 millimeter wide ball. And then because that is so soft, so my student need to enclose it with a hard agar. And that allow him to really use a vibrotome to visually cut into thin sections about 100 micrometers, okay? And then in the same time, this thin section will be floating in the solution, contains some cryoprotectants, and then my student can then use grid to fish it up like fishes. And then he was able to just plunge freeze this big section of human brain tissue and with vitrification throughout, okay? And this is how the big piece of brain tissue on a cryo-EM grid in a FIBSAM. Okay, so you see this scale bar is 500 micrometer. The thickness is about 150 micron. Okay, so then in order to do ungrid lamella generation, because this sample is so thick, so traditional gallium fib is not powerful enough. So fortunately, we have a xenon plasma fib from test can, so we were able to process this sample. So the first thing we did is by using very powerful platinum to mill up down to create trenches following the pattern of the squares of the grid and create some flat surface in front of the tissue, okay? And then this is how the front surface look like blow up. And now this surface is exposed biological material. So in order to mill in, we need to do a second time of platinum coating in front of the surface to protect that. And then once we do the second time platinum coating, we can then mill big holes in, and including some pressure releasing cut on both sides, and then finally polish it and create a big lamella with the size about 50 micron by 150 micron. Okay, and by cryo-ET on those lamella, we can see they are vitreous, although we do see some crystals here and there, so it's not fully vitrified, but in some regions we do see fully vitrified sample, and also the successful rate of creating such big lamella is very, very low, less than 5% or even lower, so I need to be honest. Okay, but when that is successful, we were able to see beautifully preserved membranous structure inside the human brain tissue. We see those membrane vacuoles, we see progression of phagophores, which is membrane engulfing materials inside the human brain, and become some dense core vacuoles inside the brain. And we can also see cross section of axon, okay, and surrounded by oligodendrocyte cell body, create this myelin sheath, okay. And so because each line is actually one time of this oligodendrocyte cell wrapping around this axon. So it contains two membranes, okay, of the membranes surrounding the cytoplasmic area of the oligodendrocyte, okay. So and then the blue means the second time this oligodendrocyte is wrapping around the axon again, okay. So our resolution allows us to look deeper into these lines, okay? So these two red lines, the first time this cell body is wrapping around the axon, so there are two membranes, and with low defocus, we can actually resolve the lipid bilayer of individual membranes. So 2 layers of membrane will get 4 lines. Those are the head group of lipid, okay? And very often we can see these 4 lines actually becoming 3 lines, okay? Means that the polar head group of lipid bilayers are pinching together, become a middle line, okay? And actually very often we only see 3 lines throughout, okay? And by doing subtomogram averaging of the 4 lines and 3 lines, we can resolve a better contrast of those lines. And in this 3-line configuration, the center line is actually tighter than the outer lines, suggesting that the myelin basic protein, which is a very abundant protein in myelin, can actually tightly tether these 2 membranes of this oligodendrocyte cell body to create insulation to help the signal transduction of axon. And this is a resolution now we can really look into human brain tissue by tomography. Of course, there are other things to consider, because after the human died, a lot of degradation happened in brain, so we need to be careful how we interpret the thing we are seeing, and maybe with some additional precautions and treatment of the human brain tissue right after the autopsy, we can start to preserve more and more structure for further study. But this will allow us to, for the parasitology field, to study okay, how parasite is acting in brain tissue, not only human, but also mouse models. Okay. So, a quick summary. So, cryo-ET allow us to really discover the RNA structure and AV and in this epicomplexum parasite and provide insight how mechanistically these parasites can secrete Rop-G content into their host. And then we were able to resolve beautiful conservation and also interesting adaptation of this molecular machine across different single-cell organisms in this Aviolata superphylum. And also, cryoplasma Fib workflow now start to enable cryo-ET of human brain tissue, okay? And this can be explored for study infectious disease and also pathology of neurodegenerative diseases in general. Okay. Okay, so of course I need to thank people. Without my beautiful group at UPenn, this is impossible. So Siobhan, Billy, Amandine, Matt, and Liam, they are the driving force of the parasite studies with collaboration with Maurice in France, Boris in our school, and Dominic in Geneva. Okay, and Katie and Ben, they are husband and wife in my lab. And then they are the driving force of making the milling of brain work for cryo-ET with collaboration with Eddie Lee in our school. And of course, all this won't be possible without all those pioneers in the room, the family, cryo-ET, and the freeze fracture replica EM. Without all those techniques in place, biologists like me will not be possible to pursue this type of interesting biological question. Just want to give thanks to all these people here. And thank you so much.
Very, very beautiful work. We have time for 2 questions.
Do you have any hint as to where the AV membranes go after secretion?
So, based on the Plasmodium data, we believe we hypothesize it's fusing with the Rop-G. So the membrane of AV is actually now at the Rop-G tip, and that fusion likely will alter the biophysical property of the region of this first neck, allow it to fuse with another Rop-G. Yeah, so that's our hypothesis right now. Yeah, yeah.
Beautiful, beautiful work. Thank you very much for the excellent and stimulating conference. So this just two questions. First, did you look into the structure of other developmental forms like perdizoids or merozoites in Plasmodium?
Yes. In Plasmodium, we look at merozoites. And then, so we are now actually also dissecting mosquito to study the sporozoite form in mosquito. And they have very different structures, and they mature from the mosquito gut all the way to the salivary gland to become infectious for humans. So we are also studying that by really dissecting infected mosquito, take them out and freeze to cryo-ET.
And the other question is regarding the comparison that you did with the ciliates. So we see that in ciliates you have the alveolar sacs. They are flanking the trichocyst discharge, right?
Yeah.
So and controlling calcium and all this. So do you see any relation with the inner membrane complex?
We have not conducted cryo-ET on ciliates yet, so I do not have data to do this side-by-side comparison of cryo-ET images. But we are now in the process of setting up cryo-ET for ciliates, so I can answer that question after we've done that. Thank you.
Amazing work, but I was thinking, when you was talking about the Plasmodium, the subgroups were whether twice fused or rapid. When the cells are exposed to the treatment drugs, does that subgroups increase or decrease in size, or the rate still about the same?
So the question is that whether or not the Rop-G size decrease before and after fusion?
No, I'm saying when you look at the groups, there was a few where it was rapid and FUS were fused, but they were less prevalent.
Mhm.
When the cells were treated with drugs,
Uh-huh.
does that group becomes more prevalent or
Uh-huh.
less prevalent?
Treated with drugs?
Yeah, the routine drugs.
Yeah, we haven't tried that yet, but it's a good idea. So we can compare different conditions of treating the parasites and then see what's the effect of different type of drugs.
Yeah,
Yeah.
that's because that may be a stress response or something like that.
Mm-hmm. Yeah, I see. Yeah.
Thanks.
Thank you.
Okay, Chang, I had the opportunity to visit you a few months ago in Pennsylvania, and you showed me most of these results. But I have two questions.
Yes.
One, did you see any connection of the micronems, not the Hopters, in association with the inner membrane complex? That is the first question. And the second one, I would like if you could talk a little bit about your recent work showing actin filaments in Toxoplasma gondii that you just published in Nature Nature Communication a few weeks ago.
Yes. Thank you for the questions. The first question is that the micronemes are the yellow vacuoles I show in the segmentation. It's a second type of secretory organelle inside the conoid. Okay, I did not focus on them today. Those are organelles secreted before rupture secretion, and making the anchors on the rupture parasite for them to grab, create this tight junction. Okay, so we do not see the interaction between the microneme and the IMC. Okay, because there is subpellicular microtubules, those microtubules in between. Okay, so we do not see them, but we do see tentative interaction of micronemes with those microtubules spreading out. We think there are some things helping those micronemes to move forward and loading them into the conoid. Very likely are some dining motors. Okay, so but it's very premature. And the second question is about the F-actin. I don't want to go back to the slides, but I say in the beginning, the ring is actually moved from the tip of parasite to the bottom by ectomyosin motors. So to provide more detail, those are actins, okay, inside the parasite, anchors through the parasite membrane onto those rings, and they are myosins anchoring on a stationary surface inside the parasite. So those myosins walk those actins backward, and because of the ring is now connecting to this actin, so when the myosin walking this actin backward, this in turn moving this ring across their cell body. That's how they invade. Okay. However, before there was no clear imaging indication that F-actin is actually present as a linear form with long strands inside the parasite, and also don't know where does those F-actin being generated at the tip of the parasite. But by conducting cryo-ET on these parasites, we were actually able to visualize individual F-actin and seeing where they are being assembled, actually on one of the two rings I showed in the beginning of the cell, of the talk, and we were able to identify actually the location of actin-seeding protein called foaming. Foaming is a protein which promotes the growth of F-actin, so we were able to really image in the wild type and also image in the cell with foaming knocked down and see the different densities on the structure of this ring to pinpoint this is the origin of F-actin and how they are sending the F-actin into the cell body for gliding motility. This is a quick summary of your question. Yeah. Yeah. Yes.
And I wonder what would be this actin doing at the posterior tip of the protozoa.
Yeah, so we don't know. We see a lot of actin accumulating there, like a cup. I think this is just a product of after they move all the F-actin backward to conduct their movement. They are waiting there to be recycled, because the way they are being recycled is to depolymerize into individual global actin called G-actin, and go back to the cell surface tip and then recycle, become new filaments. So we think they're just waiting there to be recycled, but the speed of recycling is too slow. That's why we see them.
Okay, any more questions? So, thank you again, Dr. Chang.
Thank you.
Hi, so we are free to have a lunch, and we can come back at 2:20, I think. Okay? 2:20.
Ok. Let me see. Ok. Everything's okay? Tranquilo. Pronto, pode começar. Tá bom.
Brasileiros muito fortes para a cesta. Desde a medalha pan-americana, conquistou outra individual, não vai a gente confiar no brasileiro nessa modalidade última do espetacular essa modalidade. Vamos lá, meu irmão, está ligado em tudo que acontece. Você falou que você ficou interessado em saber a agenda do esporte pela sua cidade, tem que recomendo muito mais. Se você quiser saber a agenda do esporte nesse palco, eu quero não para embaixo da sua tela, você vai ver modos e mercados especiais desse palco com a publicidade, beleza? Então, ó, final da pois é, cidade. Olha só, não precisa esperar. Perfeitamente. Já na tela para você, imagens do triângulo, mano. Quilômetros de corrida. E agora é hora de torcer pelo Brasil, torcer contra o Mundial. Final, terceiro.
So good afternoon, everyone. We will have now the sponsor talk. We can see that it's Yuri Abud. He is a specialist at the Laika. And he was invited by ARPIA to give a brief presentation about the platform Cryo, the confocal stellaris from Leica. Okay, so Yuri, you have 20 minutes, right?
Okay. Okay, 20 minutes.
Yeah, you can start.
Okay, let's begin. So, good afternoon. First of all, I would like to thank you for the invitation, both the organization of the event and the ARPA, our National Confocal Microscopy representative. My name is Yuri Abud. Today I'm an application specialist at Leica Microsystems. I'm responsible for the entire line of the optical microscopy and sample preparation for electron microscopy tools. Before Leica, I was a researcher in Rio de Janeiro, and I bet that if I were there in person, many faces would be familiar. Unfortunately, I tested positive for COVID, and I thought I didn't show many symptoms. I chose to protect people and stay home. So today, remotely, I will show our confocal cryo solution, a brief presentation about the confocal cryo solution of this platform named Stellaris 5 with cryo stage. So let's begin. Why cryo-electron microscopy? So a brief introduction about this. Cryo-EM is used to understand the molecular mechanisms in the cell, and one of the techniques dedicated to cryo-EM is called cryo-electron tomography. The cryo-ET can resolve proteins, and the interaction in the cell don't last to them 1 nanometer. So it's a very powerful technique. Here we have an image showing a cryo-electron tomogram. In purple we have some nuclear pore complex, in white some nuclear envelope, and in orange some proteasome. So this is an example of a cryo-EM tomogram. So back to cryo-ET. Cryo-ET is a very important technique, helps to find potential treatment sites for disease. Here we have an example in Huntington's disease. Huntington's is a serious neuronal disease, and was discovered that a protein involving Huntington disrupts the correct production of protein, distorting the endoplasmatic reticulum. In this image we have in blue the protein linked to Huntington, and in red the reticulum, the endoplasmatic reticulum. So this is one more example of the importance of cryo-ET. So why a cryoconfocal? Well, if you have a cryoconfocal, you can use this button to visualize and find structures of interest using fluorescence. So, and you can retrieve this image with the coordinates through electron microscopy. Here we have an example of a workflow where the sample is taken to the Stellaris, the recognizer of using fluorescence, and the lamellar region is established, and finally the sample is taken to a focus ion beam microscopy. This is a very common workflow with the cryo-Stellaris. For us, it's important to mention that our platform combines efficiency, precision, and safety. Well, there's a great thing that I was able to see all of this myself. A few months ago, I was in Germany, in Heidelberg, with the ARPA tool, and I can see and operate this platform and many other platforms in Heidelberg. And the Stellaris Cryo platform was one that particularly impressed me. It was a very powerful platform. Here we can see the efficiency in action. Here we have a video. With the Stellaris platform, we can quickly check the integrity of the carbon grid coating and get a good overview of the sample. Here's an overview of the sample. And with this overview, we can quickly identify regions of interest of our sample. For us, is a statement that early validation of the sample in our workflow reduce costs and, of course, reduce effort. Here we have these examples in a more visual form. We have here in one an image showing the carbon layer integrity. Here in two, the distribution of the samples in the grid. In three, an example of a region of interest. And again, the same statement. Now we come to precision. In this image, we can see the precision of the system. We have a confocal image with a super resolution method called lighting. Lighting is a feature of our system. In this image, we can easily observe both structures of our interest. We have in green some mitochondria. We have the mitotracker in green. In red, we have some lipid droplets. And in magenta is the positional beads for the image. So we have a system with super resolution in cryomicroscopy. You can easily identify your target with a high precision. And now we come to the safety factor. We have here some examples of features that improve the security of and the reliability of our platform, and all these factors are linked to safety. This system guarantees these 5 samples at all times and minimal contamination during all the process involved. Processes such as loading samples, transferring samples, and of course taking image. This is a statement. In your pattern, you can increase the reliability of your workflow. So, student safety. Here we have an image of our sample transfer solution. You put the liquid nitrogen in here, in this white box. This system guarantees a safe and reliable sample transfer with optimal cryo conditioners, and it's very easy to use. And to begin the end of our presentation, we are going to demonstrate an example of a workflow using this platform. Here we have a workflow with a sample cryofixed in a plunge freezing, our AMGP2, and then transfer it to a cryoconfocal, and then to a cryofib. All that with all the metadates of localization. And this workflow exemplifies the integration and the reliability of a sample with our preparation line, such as the EMGP2 plunge freeze. Here is an example of this integration of our hardware. In this image, we have a grid holder uh, which is compatible to our system, the Stellaris platform, and with FIB2. There is no need to manually manipulate the grids, so the system is very safe to your sample. Here we have another visualization of our sample transfer system. We have here images of the cartridges, the grid holders, and the transfer shuttle, our transfer system. This transfer system shows that the sample is always in the ideal temperature. A very reliable system. For us, it is always a very important statement to note that images with positional metadata can be read in the software thermoscientific maps, a very used software in cryo-EM. So you can guarantee the position of the region you have chosen with minimal alignment. All these increase the reliability of our system, of course. And now to really finalize things, we have some tables showing features presented in our platform and the internet benefits. Our platform is a upright microscope with a fixed stage. We have motorized XI stage. We have a smart touch panel for easy to use. We have a motorized camera tubes and high sensitive cameras to make images in wide field too and to build overviews beside confocal microscopy. We have a very reliable light source with LED and a stabilization table. And I would like to highlight our specialized cryo objective with an aperture number of 0.9. This is the higher number of aperture in the market for cryo objectives. So it's a very powerful cryo objective. And beside that, we have a cryo stage. We have the nitrogen storage solutions. We have our cartridges, our grid holders, and our transfer systems. That's it. It was a short presentation. I would like to thank you once again to the organization of the symposium for AFIA. And here is a QR code with all my contacts. I can answer any question that appears in my contact list, there's no problem. And of course, you can always get in touch with Harper by speaking to Manuel or Matheus. So that's it. Thank you.
Thanks, Yuri, for the talk. Do you have any questions?
Using the Leica system during your workflow, at which point do you clip the grids? Before going for confocal fluorescence microscopy or just after field milling? I'm not sure about that. I don't have any experience with that, actually. Did you hear my question?
No, I don't hear. Can you repeat the question, please?
At which point during the suggested workflow with the Leica system do you clip the grid for the autoloader? Okay.
Let me try. Yuri, he asked at each point of your workflow, they should clip the grid before or after the FIB milling?
You can clip after, there is no problem. You can use our clip station, clip after.
Okay. we have a discussion here about when is the best time to clip the grids. Do you have, I think Matthias maybe, we have another question, just a minute.
So perhaps I missed it, the lightning technology, as you called it, so that super resolution, what is it based on, and what are the requirements, and what's the ultimate precision there that you can achieve?
So if it, it's about the lighting here. The lighting is a deconvolution system. It's a very fast deconvolution system. We can get a resolution up to 120 nanometers with lighting. The very fast system, but it's a deconvolution system, a post-processing system. Well, 120, something like that.
Okay. Do you have any more questions? No? Okay. Yuri, I think we can finish now. Thank you so much for your talk. And people have your contact here.
Yeah.
And, see you another
Okay,
time.
thank you.
Bye
See
bye.
you. Bye.
So now we will move to the oral presentations.
Hello, everyone. Now we will begin our sequence of oral presentations, and the first one is Moara Lemos from Instituto Pasteur. She will present the lecture about protein photopatterning provides the morphological control for nanometer scale dissection of cell-cell interactions.
Hello, good afternoon. So, thank you, Mira. Thank you for a presentation. So today I'm going to talk to emphasize a bit more the sample preparation methods, but before the sample goes to the microscope. It's a bit a mixture of both, but it concentrates more to the positioning of the cells to specific locations on the EM grid. So in a tissue, in a tissue, the epithelial cells, they are confined in a microenvironment composed of the neighboring cells and the extracellular matrix. Those microenvironment highly influences the cell nanoarchitecture and other aspects of the cell behavior and function. When we transfer those cells to the regular culture conditions, the cells, they found a vast and rigid environment composed of glass or plastic where they grow as monolayers. And this environment has little in common with their natural microenvironment. So we have one challenge on growing those cells on EM grids. This is because we have to find a good cell density to seed the cells on the EM grid in a sense that we don't have a very low density in the sense that we are going to have very few candidates to do our data collection, neither to have a crowded environment with high density cells where they can accumulate over specific regions of the grid and they can impair the vitrification process. So even in a low density environment, in a crowded environment, these cells, they do not only grow on the carbon films in the region of the grid square, but they like to grow over the grid bars, limiting our data acquisition. So one way to solve this issue is to do the micro-patterning techniques. These techniques, they spatially position the cells on specific regions of the grid. And in this technique, we can also modify the chemical composition of the carbon film, attracting the cells to grow on specific regions in the way that we can restore, at some extent, a more closely environment from where the cells are coming from. So our group is using the photopattern technique in a maskless method. And briefly, this method consists of to apply a layer of biofilm made with polyl lysine and polyethylene glycol, which is not attractive for the cell attachment. And then we project a mask, a digital mask, made with any geometry and any size. And then we project the UV light and add a photoinitiator that will cause the photodegradation on the area projected. And then we have a free PEG layer. Then we can absorb some extracellular matrix protein, which are attractive for the cell growth. As I said, any shape of the patterning can be plotted. Here they use the circular small and larger one and the square ones. Also, different proteins can be adsorbed. This can be conjugated or not with fluorophores, like this, depending on the goal of your study, if you need to see the pattern region or not. Here we used Oregon green conjugated with gelatin and also fibronectin conjugated with rhodamine. Then we incorporated our micro-patterning technique into the cryo-ET workflow. And then this is, as was mentioned here, is a very expensive and laboring technique. And then that's why it's really, it's really important to give careful attention to the sample preparation to have at the end of the workflow a high good quality. Then we, in this presentation, I'm highlighting our optimization of the photo patterning in a completely contactless manner. This is important because the photo patterning has several steps that we can handle in the grid, and this can deform the grid and break the carbon film, even reducing the area that we can do our data acquisition. So we customize some PDMS platform that accommodate the grid on top of it, and this set was supported by the glass cover slip. Then the grid is rendered hydrophilic, and we add another ring made with PDMS higher than the central platform. This ring consists of 12 millimeters of diameter, and this acts as a hydrophobic barrier for avoiding extravasation of the solutions during the rinsing steps, and also help us to work with minimal volume reagent, helping us to save this reagent. And at the end of all of the steps of the photo patterning, we can protect our grid with a round glass cover slip, and then this can be used for transportation, or we can do the patterning through the glass cover slip, and this didn't impair the patterning. We projected a mask of a matrix of 10 by 10, and then we projected this square pattern made with the adsorbed with fibronectin and rhodamine, and we grew some fibroblast cells, and those cells, they assume the shape of the pattern. We tested different cell lines, and all of that behaved the same. Of course, you have to play a bit with the pattern, not doing some crazy geometries, but the cells, they used to follow the shape. Then, once you can play with this, we determine the best regions on the 200 mesh grid to do our data acquisition. Because we know that depending on the region, the grid bars, they can obstruct the field of views, and even the grid edges or the clip rings, they can block our view during the data acquisition. So we tilted our grid in a range of plus and minus 66 degrees, and we took pictures and measured this distance. And we realized that from that 20 microns from the grid bars, we can do a tilt range of plus and minus 66 without any obstruction. With this, we can maximize our data collection, increasing the efficiency and the coverage of our tomography. But then, we also wanted to have not only one cell on the pattern. We want to work to study the cell-cell interaction, and we want to accommodate a cell pair in our pattern. So we plotted a larger pattern in which we have 50% of those patterns filled with a single cells that was not interesting for us, and other around of 10%, there were multiple cells filled those patterns, and then we have a rate of success from 9 to 25%. And we use a strategy that the central area of the patterning, it was filled with the biopassivation layer composed of the polyallyl and polyethylene glycol. Like this, we try to induce the cells to attach from the borders of the pattern and grow in direction of the center of the grid square. To verify, like this, we have the cell-cell interactions region in the center of the grid square. And we produced some cell lines that were expressing alpha-E-catenin tagged with EGFP. Like this, we checked the maturity of the cell-cell contact sites. These numbers, like from 9 to 25% of rate of success, having this doublet in the square, seems low. But compared with our workflow of during the presentation, you're going to see that it's actually a good match for what we want. So the photo patterning at the nanoscale, it's a poorly understood environment. And also, we needed to check if the thickness of the biopassivation and the adsorbed proteins layer, they fall within the range of the electron beam permeability. So we plotted these patterns on the glass cover slip, and we used Oregon green gelatin to see this pattern. And then in the row above, we let the patterns empty just with the glass cover slip. And we characterize that by atomic force microscopy in a contact mode. And we orient the sample in a sense that the surface scanning measurements was done like first with the biopassivation layer, then the probe will face the glass, and then the biopassivation layer and the gelatin layer. And with the measurements, we observed that our biopassivation layer had 2 nanometers thick and the gelatin Oregon green with 0.4 nanometers thickness. This is almost 2 orders of the magnitude of the thickness imposed by the cryo-TEM microscope. So meaning that the photopatterning didn't negatively contributed with the total thickness of the sample at the end of the workflow. Then we characterize those patterns by the topography using the cryofib-SEM in the ion mode, and we plotted our pattern in the center of the grid square, and we plunge froze those grids. And then we see that the central area where the pattern is located, we see a depression consistent with the AFM data. And then we proceed with data acquisition. We proceed with some tomograms. And then we observe that the region between the biopassivation layer and the protein absorbed layer, we see a difference in density. And this difference in density is also observed at the low magnification images on the TEM, where they see clearly the pattern region. And then we correlate the fluorescence image with our tomogram, and we observe that the boundary between the biopassivation layer on top and the adsorbed proteins are irregular at the nanoscale and not smooth as observed by the fluorescence image. Then we took some representative tomograms to verify if the photopattern, if the confinement of the cells, they have an impact on the cell integrity. And then we checked the membranes that were intact. We can see that there is no hold on it. We found some cytoskeleton elements represented by the actin fibers here, even in internal organelles at the mitochondria, located and close to the borders of the cells. This indicating that the confinement of the cells promoted by the photopatterning didn't impact on the cell integrity. Then we wanted to explore our cryo-ET workflow doing the lamella preparation to check the compatibility with the lamella preparation and the photopatterning technique. So we plunge frozen our grid with the cells. You can see the cells are with the square shape. I selected some possible target areas. In that day, I was really emotional because I selected a lot. We just using the same automated workflow. Then we produced from 15 to 20 lamellas over 2 consecutive days of work. And then in here, I used the morphology, the topography of the cells to place the lamella position in the sense that I can see one cell on the left, another on the right, and decided that this could be a good region to do my lamella. And then the regions above and the top were removed, and then the lamella is successively polished until it reached around 200 nanometers in our case. And then this is a view by the cryo-SEM of our final lamella, and this is the same lamella under the cryo-TEM. Then we selected some places to do our tomogram because those are deep regions inside the cell, so you were expecting to find the regions that the cells were interacting, and we were lucky to find this one where we have one cell on the left, one on the right, and you observe 2 endocytic events, one in each of the cells. This is a budding vesicle endocytic vesicle being formed in here, and this is a clathrin-coated pit with the clathrin decorating the vesicle. But what is interesting to note in this cell is that the nucleus is very close to the cell membrane, and in here we depicted a nucleopore. Then we selected another region to take our tomogram. This is the low magnification region where we selected the tomogram a bit magnified, and then we managed to get a region with a cell-cell contact junction. And these, we have the elements just to compare these junctions morphologically with other ones, and we have the morphology to help us to say that this resembles to the punctum, the reminiscent punctum of the punctate adherent junctions. And in here in the cells, we also observe the mitochondria, the lipid droplets, the nucleus, and the endoplasmic reticulus with the ribosomes on the top of the membrane. Then I segmented the tomogram, we produce it, and just for you to have context, in yellow is the nuclear membrane, in orange the membrane of the other organelles, the ribosomes in blue, the cell membrane in white, and the cell junctions in red. In pink is the actin cytoskeleton, and we observed a different agglomeration of those cytoskeleton elements, forming tight bundles close to the junction region in both sides in both cells. And then when we were characterizing the punctum of the junction, we observed that this is formed by elongated rod with 4.5 nanometers of diameter, and those rods are irregularly disposed in the junction, and sometimes they form larger assemblies of 20 nanometers in length, and they bridge both cells, letting an intermembrane space, trust me, it came back. So this space is around 15 nanometers. So for us, we wanted to really characterize this photopattern technique, but as we find some interesting aspects of the biology, in the future we want to explore it a bit more, trying to find some labeling methods to tag those proteins and to use the cryoclam, hopefully the 3D cryoclam, and to improve the characterization of those junctions. And then as a conclusion, we provide the nanometer characterization of the biopassivation layer and the protein-adsorbed layer using the cryofibsam, AFM, the cryo-ET, and the cryoclam. We optimize our photopatterning method in a completely contactless manner, which is more robust and can be used for working in a multi-site equipment. And the cryo-ET validate the functionality and the pristine ultrastructure of our cells, indicated that we have healthy cells using this method. So I would like to thank the people from my lab, mainly Nils Volkmann, Dorit Heinen, and Cécile Sauvanet and Armel Bezot that helped me with this workflow, our collaborators from Santa Barbara and Citium Institute, the facilities from Sanford and from Pasteur. And also I would like to give a special thank for Professor Vanderlei, Professor Adalberto, Kilder Miranda, and the people from the Senabio that are hosting me from this year in Brazil and allowing me to participate this very bright moment in the electron microscopy in Brazil. So thank you all for your time.
Thank you, Moara. Someone would you like to question? Someone would like to question something to Moara? It's the time. Okay, a moment.
Thanks. How does the masking work in the micro patterning? What actually gets in front of the light beam to create whatever pattern you want?
Hello, hello, hello? Yeah, okay. So we use it like a softwares, like the Inkscape, and we design a pattern. So people are doing different patterns like stars. People from Alveol, which is the company, they did an Eiffel Tower because it's a French company. So we project this pattern that you want, and then it's done. It's in there. And more, just a complementation, more recently, there is 1 or 2 studies that it's using not only the extracellular matrix protein, but antibodies to select different cell types. Like this you can have in the same grid, like if we use the finder grid, you know which cell type you have in the exactly position, so we can play a bit more.
So how do you draw the Eiffel Tower in a mask? What is the mask? What is blocking the light?
What is block? So you use a region that you, namely black and white. So in this case, the black region is going to be your pattern, and the white is going to be like how can I say that? A negative that prevents the light to be projected from there. This is digital. I'm not sure if I respond to your question. Yeah. Yeah. Yeah, you have the shape of the light from when you projected the UV light. Shape of the pattern.
Thanks for the talk. For how long can you keep the cells in the micropattern material? I mean, incubating for following processes that can take longer, like days or.
Like for the cells on the grid, that depends on the cell type, because there are cell types that grow during 24 hours, 48 hours, so they are more fast or slow. But the photopatterning without the cells, you can keep them in like a PBS solution for 15 days.
We have one more question from Dr. Chan. Chan, okay.
Thank you. So great talk. So yeah. So first, answer Grant's question. Actually, the pattern is made by a tiny array of small mirrors, so they can control particular set of small mirrors
So
to
sorry,
create a patented light.
With a digital mirror device, so the mirror play with the light.
Yeah. So there's an array of small mirror in the path of light, so you can selectively reflect different shape of light into each square of grid. So what kind of grid have you tried? Which type of grid will you recommend?
We tried with amber grids. They are 520.
520?
Yeah.
Okay.
So those are amber grids from Quantifoil. So this grid is subdivided from 9 squares with 25 small squares inside, like from A to H.
Mm-hmm.
And then from the A big square, you have 25 small ones.
Oh.
So like, yeah, this is a very nice grid to work with Clem.
Thank you.
Thank you, Moara. The next person to talk with us is Dr. Mariana Longuinho. She's from CBPF. She will talk about glycine influence on calcium carbonate growth, a study by advanced electron microscope techniques.
Good afternoon. We will show you some the latest results from the project that I'm working on. We work a lot with calcium carbonate, and we are trying to understand the effects of amino acids on the nucleation and crystallinity of the polymorphs of calcium carbonate. Why studying them? Calcium carbonate is the most abundant mineral in the nature. There is 3 main polymorphs. The less stable is vaterite, the more stable is calcite, and the one that we find more in nature also. There is another polymorph also that it's calcium carbonate monohydrated, ICAIT, and the amorphous phase that can be hydrated or unhydrated. So the difference between the mineral that we find in nature and the one that we synthesize in laboratory is that the fact that in nature they are surrounded with organic molecules. And this kind of molecule will change some aspects of the crystal, and we are trying to understand how. And why studying the amino acid single is because we saw that many proteins are rich in some kinds of amino acids. So we are trying to understand how they will affect this process. We already published a paper where we could understand better how aspartic acid will influence on nucleation growth, where we could see by in situ electron microscopy that the aspartic acid forms a chelate with calcium and carbonate ions, and it leads to a microenvironment where the calcite will grow. And now we are trying to understand glycine, that it's the simplest amino acid, but we can see that make a huge difference when it is in the media. There is several papers that show that the lifetime of the amorphous phase will change, and glycine used to stabilize the vaterite polymorph, that's the less stable one. But we don't see how the glycine will influence the formation process. And that's what we want to understand. And that's why we are using some electron microscopy techniques like in situ, like cryo, to better understand this process, since the mineralization is a really fast process, the nucleation. And this kind of technique will help us to better understand this phase. First of all, we did some other techniques, not so complex as electron microscopy, and we could see that if you have a reaction between calcium chloride, sodium carbonate, and only, like our control, you just have calcite. But if you add the glycine together, it will have a mix of calcite that you can see here and vaterite. So the thing is, glycine will stabilize vaterite, but also it doesn't inhibit the formation of calcite. Besides, by DTA, we could see that there is an exotherm peak when glycine is in the media. And so this indicates a phase transformation during the process. It's just after 400 degrees, sorry. That's when glycine used to degrade. So we think that probably glycine is going out of the crystal, so there is a change of phase. And this can indicate that glycine is in the crystal lattice. So after that, we did a in situ TEM, a liquid phase. The holder is just a holder from a TEM, but the thing is there is a capillary inside that goes to the tip, and the tip is a bit different from conventional one, where you have a rubber ring and two wafers where the liquid can pass through or be confined here, so we can analyze by TEM. And here is a schema where you can see there is the upper and the bottom wafer. Here there is a space where you have the liquid, and you can see the reaction through this silicon nitride membrane. By the way, it was all in collaboration with IPCMS that I did during my PhD. So we could see that we have rounded particles, and during the time they increase in size, and they also start to have a diffraction contrast in the edges, like you can see here. And after that, they go expanding, and you can see there is another ones close to them. And it disrupts and form like a nanocrystal chain. I don't know if you can see it right here happening and here. And this one is from another area showing that this was not an electron beam effect. It was happening in the whole reaction media. And here, another thing that we saw is the growth of small crystals close to bigger ones, like you have the crystal already stabilized, and then there is another one, a tiny one growing close to it. And you can see them moving here, like there is a reaction occurring. And very interesting, there is like this vaterite crystal, and there is another one here faceted, and you can see like this one is growing while the vaterite is getting thinner. So these interactions lead to the growth of maybe the more stable crystal. We also did the diffraction, of course, to make sure that we were seeing a vaterite, and the pattern was vaterite. And of course there is, I put this video here to show that we can't focus the electron beam too much time because it has an effect. There is heating and another reactions occurring, so there is of course a right way to record these results. So at the beginning of the experiment, we saw this kind of structures. There is a contrast, and there is little crystals growing in this region. So we are trying to understand if this is a dense liquid phase that is common in pre-nucleation clusters, or this is a chelate, like glycine is interacting with carbonate and calcium ions like L-aspartic did. So we are in collaboration with a researcher that studied computational simulation to help us to understand what's actually happening. And in the end of the reaction, we could see that not only not only vaterites formed, but also a lot of calcite and many calcites attached to vaterite. So after that, we try to understand better with cryo, since we can freeze the moment and analyze better. So we did using a Vitrobot at Lab Nano in CBPF. We freezed in liquid ethane, and then we went to the microscope, and after 10 minutes of reaction, we could see an amorphous phase, and a really big amorphous phase. They were between 1.5 and 4.6 micrometers. So it's a great result that shows us that indeed glycine, when it's in the media, it stabilizes the amorphous phase. And this amorphous phase we only can see in liquid phase. When you dry, it disappears. So it stables only in the liquid media. Here is the DDS showing that, in fact, we are seeing calcium carbonate, and probably this amorphous phase may be the precursor for the rounded shape particle that we saw at the beginning, at the video in situ, where after it grows, they start to have like the diffraction contrast and leads to the nanocrystals. We also observed that there is two kinds of vaterite. in the media. First one is this vaterite that it looks like it's composed by many nanoparticles here, so we did the lamella to understand better what's happening. We saw that there is some nanoparticles that are very oriented. We can see like organization here, and here, and here. And also this kind of vaterite that is always attached to a calcite. And we also did a lamella. Here is the calcite part, and this is the vaterite one. It's a conventional lamella, okay? It's not a cryo, I'm sorry. So we saw that the porosity of the vaterite, the single one, it's much higher than the one attached to the calcite. Like the one attached to calcite is more, the material is more compressed. And after analyzing the electron diffraction, we could also see that the red one is the vaterite attached to calcite. It has like a crystal habit. You can see that the diffraction shows a better organization than the vaterites alone. So maybe this is it can be the reason why vaterite is attached to calcite. So it's more organized, and this material is leading to a more stable phase. We are trying to understand better this part. So this work, we could conclude that glycine acts slowing down the reaction speed, increase the lifetime of amorphous phase, but only in liquid environment, stabilize vaterite, but don't inhibit calcite formation, and the glycine is embedded in the crystal lattice. I wanted to show only the electron microscopy results, of course, because of the theme of the symposium, but we have many experiments, and now we are starting the computational simulation exactly to better understand this mechanism. But both techniques, in situ cryo, were great to help us to understand this first moment of the nucleation. Okay, I want to thank CBPF in Lab Nano and IPSMS for the infrastructure and for PERJ. So you all, thank you.
Thank you, Mariana. Do someone have a question? Okay. The first one.
Hi, thank you. I just have a question about the holder that you were using to monitor the reaction in liquid phase, right?
Yes.
So what's the thickness of the sample? Can you give like just the dimensions of the actual sample?
Yeah, like the wafer, we have the thickness of the wafer, this space between, and it varies from 100 nanometers to 500 nanometers. For example, for control experiments, we had to use the 500 nanometers because it grows very fast. But this one, if I'm not mistaken, was 100 nanometers of space.
So like you're using inorganic materials, so you don't have the problem with radiation damage that a biological sample would have. But I wonder, can this kind of holder be used to look at a biological sample? I know that, yeah, I mean, taking care of the radiation damage and the motion in liquid, that you don't have a problem when it's frozen. But is there any application to look at like large structures or something?
I believe so, because if I'm not mistaken, Professor Farina can correct me, but there was one student that went to IPSMS to study bacteria, right? Magnetostatic bacteria, and he had some great results also. So I believe that you can use also for organic material.
Would you like to question? Okay.
Uh, uh, do you have any evidence that glycine is being incorporated into the amorphous calcium carbonate, or do you think it's just like a surface effect?
I believe that is, yeah, the amorphous phase, I'm not sure, but we have some use results that it indicates that it's probably in the crystal lattice. But yes, in the amorphous phase, not yet. We are like continuing with cryo exactly because we can see the amorphous phase now. So, but this is something that we are working on.
This might be like very interesting looking in the other way around, like the effect of the crystal into the amino acids. It can be relevant, for example, into some like prebiotic chemistry studies, for example, how it's affected, for example, the polymerization of amino acid chains in an abiotic environment.
Yeah, it's
can be very interesting. Congratulations
yeah.
for the talk.
Mm-hmm. Thank you.
Thank you, Mariana. Now the last lady of this afternoon. Now, we have Dr. Indra Augusto from here, Federal University of Rio de Janeiro. She will talk about exploring the interaction of acid-calcisomes with mitochondria in Trypanosoma cruzi by cryo-electron microscopy.
Hello, everyone. Good afternoon. Thank you, Mira, for the introduction. And I will talk today about our recent data showing the acid-calcisomes and the mitochondria in the cruzi and also the interaction between them using cryo-EM at higher resolution and also cryo-electron tomography. So first, just to know and remember about this cell model, the cruzi has a medical interest because it's the parasite that causes the Chagas disease, tropical and neglected disease endemic of the Latin America that affects millions of people around the world, and but it still need for better treatment because the only two drugs available have limited efficacy and also strong side effects for the patients. The cruzi is a parasite that has a complex life cycle that alternates between two hosts, the insect vector and the mammalian host that can be us. And I not go in details of this, but I want to highlight and that you keep in mind that the cruzi has three different stages of development. One is the epimastigote. There is the replicative stage of the in the insect vector, in the invertebrate host. Then it differentiates into the triple mastigote, that is the only infective stage able to invade the mammalian cells. And there this happen other differentiation stage. The triple mastigote goes to a mastigote form, and that is the replicative stage in the mammalian host. The cruzi also its interest because it belongs to the flagellate protozoa, early eukaryote, and making them a good model to study basic cellular events in eukaryote overall. And comparing to the superior cells, superior eukaryote cells, the cruzi share most of the structures, organelles, but it has some specific and distinctive structures, and I will only highlight today about the acid-calcisome and the mitochondria. So the acid-calcisome are one acidic and electron dense organelle when we observe by TEM, and this electron density came from the lumen that is rich in polyphosphate and different ions. Between them, the zinc, sodium, potassium, and magnesium and calcium. That is the two more, the ions with more concentration inside the organelle. And recently, our research group described that these ions are not random distributed in the organelle, in the acid-calcisome, but they are organized in nanodomains with specific spatial distribution inside. And this will be better explained by Kilde tomorrow in his presentation. Sorry, I'm a little bit nervous. So this organelle also has a lot of proteins in the membrane, but like aquaporin, ion exchange, ion and proton pumps, and ion channels that are important to keep the characteristic of the lumen. And I want just you to remember that this organelle has the IP3 receptor, that is a calcium channel, also described and present in the ER of mammalian cells. About the mitochondria of the cruzi is a little bit different because this organism has only one mitochondria that is branched and distributed along the whole cell body. Here is a mastigote cell, and you can see the 3D reconstruction of the mitochondria in green distributing in the whole cell. Also, we have a specific structure called the kinetoplast that is basically the mitochondrial DNA organized in a complex array of fibers. And in the literature, we have some evidence showing the interaction between the acidocalcome here in red and the mitochondria in green, but these evidence are only from IFA experiments and also ultrafine sections showing the proximity between these two structures. And in the same study from do Campo, he knockouted the IP3R protein present in the acidocalcome, and then they observed that the calcium inside the mitochondrial matrix reduced the level. So they hypothesized that the acidocalcome and mitochondria could interact through these proteins. The IP3R connects to the VDAC, the voltage-dependent ion channel, and then the calcium goes through the MCU, not the Marvel universe, but the mitochondrial channel uniport present in the inner membrane. So this project, the main goals is to study the membrane proteins in the acidocalcome, as well as the structure and functional dynamics, and also to explore these contact sites between the acidocalcome and mitochondria using high resolution. So to get this high resolution, we start applying the cryo-EM techniques and also the cryo-electron tomography. Here is what we have done so far. We got whole epimastigote cells because they are tiny enough to be imaged as a whole amount. So we put it in the system of the Vitrobot, and then we first did a grid screening using our microscope, our 200 kV here in Senabio, getting also single images. And then we got the opportunity to go to Campinas and get cryo-electron tomography using the Cryos, Titan Cryos 300 kV. These are our first results. So as I explained, as I said, the acidocalcome is an electron dense organelle with the membrane around. You can see here in the single image and also in the tomography, electron tomography. But what was a little bit surprise for us is that this organelle also appear with certain frequency in our analysis. As you can see here, in the same cell, you can see the lumen fulfilled, but also this lumen just partial filled that we call or partially empty as what. Here's the electron tomogram showing the same, and we observed this in several sample preparations in different strains of the cruzi, so it's a really thin inside the cell. And we also could observe what looked like be an intermediate stage between conformation between these two, that is acidocalcome with two different electron densities, one darker center with the border less electron dense, and also in this you can observe this acidocalcome specific in the tomogram showing the same, but the opposite was also observed by cryo-electron tomography with the border darker and the middle less electron dense. Here is also an interest data showing by electron tomogram the fission of this core inside the acidocalcome. So you can see with a little bit more details. We also observed this in other preparations, but with this resolution, I think this is the first time. And as I mentioned, was a little bit surprised to see this with so frequent in our sample, the acidocalcome partially empty. And that is because when we look at this organelle using other techniques like chemical fixation or even cryofixation associated to free substitution and cryosection, usually we interpret this kind of phenotype as an artifact from these techniques, but as we are starting seeing by cryo-EM, it could correspond, it could not only be artifacts, but probably also could correspond sometimes could correspond to physiological states, nature of the cells, or maybe some kind of response to environmental stresses. And also cryo-EM is revealing this complexity of this organelle that we couldn't observe using other techniques before. Now talking finally about the interaction. Here is a section, virtual section, where you can see the acidocalcium really close to the mitochondrial membrane. And in this one, we can see around 5 nanometers of distance, but it can also range from 2 to 20 nanometers of distance. And specifically in here, we can see the membranes in contact each other. So the member of the acidocalcium, the mitochondria, they connect here. And with a little bit better resolution, you can see in other cells the same. The acidocalcium close to the mitochondria with some electron densities between the membranes, probably proteins connecting them. And as I mentioned, there is in the literature this hypothesis linking the IP3R receptor, the VDAC and MCU, theorizing the calcium flux between the acidocalcium and the mitochondria. When we look at the mitochondria in cryo-EM, our single image showed also these little spots, dark spots in the mitochondria. And when we did the tomogram, we confirmed that these spots were not a contamination during the process, but the granules, there are granules inside the matrix, the mitochondrial matrix, that were already described in the literature in mammalian cells. But here we can see the acidocalcium as well, linked to the mitochondria by the membrane. He also acidocalcium close. And then we can see the granules also in the same direction, close to this contact. Here's the tomogram running. And as I mentioned, the granules are close to the membrane that are close to the acidocalciums. And also, you can see some others granules close to the cristae of the mitochondria, indicating probably the interaction and the ionic flux between these two organelles. So you can ask me, what are those granules? I cannot affirm. We don't run yet the microanalysis, but seeing the morphological characteristics, we can hypothesize that it could be the calcium phosphate that is rarely described in mammalian cells, because they have similar size, ranging from 30 to 100 nanometers of diameter. And also, here's the example of the calcium phosphate in the mitochondria of a mammalian cell. And in this work, they described the nanoclusters of these granules that are around 5 nanometers. And when we see our tomograms, we can see these little spots that could correspond to these nanoclusters that also have around 5 nanometers. And finally, our last data. Why I believe that these granules could be a calcium, could have calcium inside, is because we have this mutant here in the lab. There is a knockout for this mechanosensitive channel that is localized in the complex contractile vacuole. I didn't talk about this organelle because of the time, but the vacuole is responsible for the uptake and the efflux of the water during the osmoregulation, the cruise. And our collaborator, Veronica Jimenez from the California State University, described this channel. And they find that this channel can conduct small osmolytes, mainly chloride and calcium. And also when this mechanosensitive channel is out of the cell, is knockouted, they observe that the cell have a lower intracellular calcium level and also a lower capacity to calcium uptake, leading to a cytosolic calcium disruption. And when we analyze our first analysis of these mutants, what I first shows that the granules appears to be more interconnected than the clusters when we compare the Y type. But it's important to say that we have just few cells of this, so I cannot affirm. But I hope with the time, with more opportunities to get electron tomograms, we can see this. But if it phenotype confirm, we can say maybe it could correspond because the knockout of this channel change the flux of the calcium inside the cell, and somehow it could increase the calcium flux to the mitochondria, increasing the size of these granules. But it's something that we have to work on. So final consideration, because I think we have more questions than answers in this work. But I can say that the cryo-EM is a powerful technique that can capture these different states of organization of the osteocalcium core, and also help us to investigate the ion mobilization. That is a dynamic event. And I think you associate with the microanalysis, the cryo-EM can give us great answers about this kind of event. And the osteocalciomes, we confirm that they are associated to the mitochondria and corroborating with the idea of the ionic flux between these organelles. And also, it's important to understand this dynamic between osteocalcium and mitochondrial intercruci, because it can provide insights into similar interorganelle interaction in other eukaryotes. Like I said, the IP3R receptor is also present in the ER in mammalian cells, and there is also a connection between the ER and mitochondria. And so if you figure out a little bit about this intercruci, maybe it can help to understand better this relation. Our next steps will be to investigate the mitochondrial granules composition to confirm if is there calcium there, or phosphate, or polyphosphate, or other thing. And we want to study better the molecular structure organization of these contact sites. Now that we have the ACLUS, we can go with lamella production and get better resolution and try to do things like template matching, subatomic gamma averaging in these contact sites. So I'm time, and I want to thank you, all the research group members, and also all the members from the Laboratory of Cellular Ultrastructural Cellular Ertamaya, our collaborators, mainly Dr. Rodrigo Portugal from CNP, that helped me open the doors to do the electron tomography, and also the Brazilian agents and the facilities and the staff of Senabio and Elenano and CNP, mainly Adélia, I don't know if she's here, and also Mariana and Bia from the CNP. So thank you, everyone. Sorry.
Thank you, Ingrid. Has one, okay, just a moment, please. Professor Marcos Farina.
A volta vai ser difícil também. Thank you for this beautiful talk. Sorry for my question. It seems very different, the granule from the acidocalcisome from those from mitochondria. Is it, for example, do you have a core that is growing like inorganic crystal growth, like, for example, pyrophosphate? I don't know about acidocalcisomes, but the type of images that you showed, some are dense, surrounded by something that could be for some biological crystals, hydrated environment, etc. But it seems that you have a core that is growing. So it's not, of course, an artifact. But in mitochondria, it's completely different. So aggregation of aggregates of small nanoparticles, probably much more calcium in the mitochondria for known reasons, and I would say some structured phosphate molecule. Is it crazy, this possibility?
So in ácido calcium, we have more than the calcium. So you have calcium, sodium, magnesium, and polyphosphate. The polyphosphate works at keeping together the other ions. And when we are what we have about the ácido calcium are more using other techniques and not cryo. And this data that you mentioned, the difference, the kind of growing in the core that we're seeing with cryo is the first time. So I think that now we can try to understand better how this core keep together and how it grows, how the biogenesis of the ácido calcium, we don't know. And in mitochondria, yes, I believe that is less ions. So our main hypothesis is calcium and phosphate, because it's what is described in other cells. And in this case, it will be different, because the ácido calcium has more complexity than other elements as well.
Leo? Hi, Ingrid. Congratulations on your presentation. Beautiful data. So one thing that I was very curious about is that you showed that the electron dense inclusion that we used to see inside ascocalcisomes, we believe that that was just artifacts, and you just showed that these are not artifacts. And then you showed from Wendell's paper that there are nanodomains for the chemical components of the ascocalcisome. So this electron dense inclusion does not correspond to these nanodomains, because they are not lost. I mean, these images are very different, right? Because the nanodomains show that calcium, magnesium are in these nanodomains, and the electron dense inclusion is another different thing. Is that correct?
No, the electron dense is all together, all the ions and polyphosphate, all the nanodomains together when we see in the TEM. And maybe when this is partially empty, this one that I showed, in that small core, we have nanodomains there, but as I said, I have to put microanalyzing these different partners to see what is there. Cannot affirm, but yeah, it's a question to answer.
Okay, and a second question, I mean, it's just more, have you thought about, because you mentioned that maybe this connection between the ascocalcisomes and the mitochondria would be important for calcium influx. And have you thought about maybe proton influx, because between the two membranes in mitochondria, there is a higher concentration of protons. So,
yes.
And as the ascocalcisomes are acid too.
Yeah, good point. I didn't thought about this. Could be. I mentioned these three proteins because it's what we have in the literature, but could be other thing, other kind of channels there that we don't know. Could be also proton flux. Something to investigate.
Okay, thank you.
As I said, I have more questions than answers.
Any other question? So, thank you, Ingrid. And I'd like to invite everybody to a coffee break outside.
Don't get nervous.
I'm not nervous. I'm frustrated.
Why are you frustrated?
When I see all these distracting talks, and then I think of mine. Just exactly when Ingrid left, I want to check if my Maybe not. If everything is okay with the cable, I don't need.
emenda para ele se a gente propõe alguma coisa.
Não, olha só. Hello, if you could take your seat, please. Hi, so let's proceed with our last talk for the day. Continue with our program here. So it's a great pleasure to have here Dr. Bruno Humble. So Bruno is an old and dear friend, which knows everyone here in Brazil, has been here many times, organized the cryo-EM course here together with Roland, and it was really a pleasure to have him here. So just a brief introduction of his academic training and research interests. So Bruno Humble did his doctoral research with Hans Mohr and Martin Miller. So those that are from the area know that they are really cryo specialists. So developed a lot of tools with freeze fracture, high pressure freezing. So he had his PhD in natural science at the ETH in Zurich, and followed by a postdoctoral fellow in the Institute of Pathology and in the Department of Cancer Research. Then he moved to the Max Planck Institute of Biochemistry in Martinsried. I think that this is a stamp of quality. Everybody that goes to this, this is the stamp that we know that It's really important. So then he moved to Utrecht in the Netherlands, which is also a place that we know that it's very, very important in the field. So he has been around a lot of places. So he took a sabbatical year in Japan. He has connections with Japan, as you can see in his projection here. Then as assistant professor at Utrecht University from 1999 to 2006. I'll skip a few things here, Bruno, otherwise I'll stay here all the afternoon. So, and then finally, I'll skip like 10 years. Finally, he moved to Okinawa, where he first worked as the head of the imaging group, then as a visiting professor in Tokyo, Japan, and then since 1st August last year, he's an expert at the Provost Office of the Okinawa Institute of Science and Technology. So Bruno, thank you very much for coming again, and we are eager to see what you're going to show us.
Hillary, thank you for this nice introduction, and especially I would like to thank Wanderlei, you and Carolina and Marsha for bringing me here back to Brazil. I haven't been here for 4 years. The last time was 2019 when we had our course in Minas, in Belo Horizonte, and yeah, but a few. Unfortunately, I'm bad at names, but a few people invited me twice to give a Zoom meeting here in Brazil from Okinawa. Okay, yeah, it was very difficult. Well, first I have to say something else. I'm really astonished and I feel very much honored that I may be here, because in these 2 days I heard much more interesting stuff and much more things, advanced things and good quality talks than I heard in 1 week at the international meeting in Korea. So it's really, thank you for organizing such an excellent meeting for me. Okay, yeah, what you see here is the castle of the Ryukyu kings, because Okinawa was not really Japan, it was annexed by the Japanese. So before it was an independent kingdom, and to the big sorrow of the people from Okinawa, it burned down on 31st of October 2019, and they are trying to rebuild it. This was when I went there for my job interview. I could get a picture and I save it dearly. Now, I didn't really know what I should present here because I didn't do much new things lately. I was just sitting there and trying to keep people happy, but there are a few things we still did. So one is cryogenic electron microscopy, and there I always like to say, like a virgin becomes a child, I as a nowadays cryo-electron microscopist became PI of a national grant for cryo-electron microscopy. As you see here, it has become a big network of let's say the original center, of course, is somewhere here in Tokyo and Osaka. These were the big centers of cryo-electron microscopy before. And with this national grant, the whole network was extended, so they have now high-end microscopes up in Hokkaido here, or down here in Tohoku, but also in Kyushu at the Kyushu University in Fukuoka, and so forth. And one of the very first, or I think it was even the very first, cryos in Japan was down here on this small little island. And this is Okinawa. That's where we are. And this is how the university looks like. Yeah, Okinawa is really small, 1.4 million inhabitants on all the islands that belong to the prefecture of Okinawa. And the island is about 104 kilometers in length and between 3 and 30 in width. So it's really, but Corona was a wonderful time because we could move around. We were not really isolated. We were banned for 1 month from the university, but for the rest, if we didn't tell anybody, we could move around, and so I discovered the island. I was going from one spot to the other. And in the first year and in the second year, with my boss then, her husband, and some of our friends, we went almost every weekend for snorkeling and barbecuing. So for us, Corona was a real relaxing time and energizing. Okay, so that's the institute. Yeah, I think that's the previous one. Now we have 2 more buildings, and I wanted just to show it to see what kind of paradise is in the background. Okay, now let's get a bit more serious. So with this grant, we were analyzing a lot of the light harvesting complexes of different phototrophic bacteria. And so this is one that's in almost the, the absorption spectrum is almost in the infrared. And what we see here is, or what we should see, let me see, I run too fast, that the complex is composed of 2 rings, an inner ring and an outer ring. In the center there are then the chlorophylls and the photoreceptors. And what turns out, as you will see a little later, is that these calcium ions here are very important. They keep the 2 rings together. And we have here on this 970, we have fully all coordinates are how do you say that? I get complication with all the languages. At all the coordinates we will find one of these calcium ions, and so there are 16 here. Then in the next bacterium, that has an absorption maximum which is a bit lower. It's 915. It is mildly thermostable, so it grows up to 57 degrees. It's also fully calcium bound, so you see it probably best in this ring here. It is also with 16 calcium, and maybe one other interesting thing of this complex is that it can dimerize. And then the next one has only, I think we see it on here, so that's the complex as we revealed it. There you see on here, it only has 6 calcium. So again, the 2 rings are a bit further separated, and again, the absorption maximum goes downwards towards blue. I mean, it's still not blue. And once more, the last one I'm showing, here is the coordinate of the calcium, and here again you see, like with the other one, I think I also, no, I didn't paint it. You also see the distribution of the calcium is very similar to the previous one. You have 4 on this side and 2 on the other side. And again, I forgot here to put the absorption, but it comes here in the table to summarize. So these are the 4 different light harvesting complexes I'm showing you. We did a couple of more, but these are the ones I'm showing you, where you can see that how the calcium and what I didn't show you, the distance between the ring, influence the absorption maximum of the light. Yeah, so this is our cryo-EM thingy, what we are doing. As I said, I'm not an expert. I cannot do single particle analysis by myself, but I have a brilliant postdoc staff member who is extremely efficient, and not only that, she's also very much interested. I had in the previous, so this grant was renewed last year, and in the previous 5 years I had another one who was, let's say, an office worker. I mean, he did good work when he did it, but compared to him, it's just brilliant. If you have such people who are so full of energy and interest, and yeah, so it's at the moment it's really brilliant to work on this. So I myself, I'm a fan of volume microscopy, and also here we have a FIB that potentially could do cryo, but I never used it in cryo. So I always only use it in at room temperature. So, pardon? Oh. Okay, so this, let's say, was standard fibbing geometry like material scientists were using. And with that we started in Utrecht. We had the first fib, and at that time Martin's Reed people came to us to see how the fib would work. And then within very, very short time they overtook us with huge speed. Okay, so we saw then that the electrons, we fib on the siding and take a picture at the inclined level, and with this you see that some of the electrons, the deeper you go, the less electrons come out because they are blocked by this kind of geometry. And so this was one of the first images, so you see very nicely the gradient we get. And in addition, we don't only get the gradient, but the image is also by cosine of 38. That's the difference between the ion gun and the electron gun, too short. So we would need to stretch every image by cosine of 38 to get the real dimension of the image. In addition, if we fib, you imagine we have now the block like this, and you go further and further in the fib. You always have to adapt the beam position because it moves, and at a certain moment that feed is finished. So you have to reset up with a new zero feed so that you can continue. But at that time, yeah, that's the milling length limit. But at that time, when we had our fib, our new fib, which was a Helios 650 in Lausanne, Cheng Zhao from FEI introduced us in how to use the fib. And he said, you should be more clever. Do fibbing like this. So put your sample on the top, and you take off the surface at the coincident beam distance, which is 4 millimeter in the Helios, and afterwards tilt it normal to the electron beam. And of course, you also know the closer you are at the pole piece, the higher you can get resolution because you have better imaging condition. And with this, we can also use the semi-inlens mode of the Helios, which really makes a big difference in image quality. So we could go closer. We were normal to the electron beam, so there was no deformation of the image. The image was as it was taken. And we could go, yeah, that's I said already. And then we go back for the next slice, we go back and so forth, and that's how we get our stacks. And this is the protocol I'm still using up today. Then, as yeah, I have maybe to say we are, as I said, since about 1 year, we are this small team, me, doing this kind of stuff, and my brilliant staff member who does my cryo stuff. And so I was somehow not really forced, but I got interested to collaborate, of course, with other universities. And definitely in looking at Okinawa is one of the poorest regions in Japan. And they are completely occupied by the US. There's 74% of the US military are my neighbors. 20% of the surface of Okinawa is still occupied. So this is one income source for the people there. And the government from Tokyo, they wanted to put some technology or something like our university there as some kind of developmental help for this small island. So that's how we came, and with this in mind, of course, I was very happy to collaborate with our neighboring university, the local university, the University of the Ryukyus. And one of the projects is this, looking at diatoms, and I don't remember who it was, but yesterday already somebody mentioned this organelle here. the pyrenoid, the place where you have rubisco, the place where you have CO2 fixation. And of course, nowadays, everybody talks about the environment and CO2 and so forth. So this is very important because the diatoms, they absorb CO2. And when they die, they sink down on the ground of the ocean. So they deposit the CO2 down on the ocean. And I was told that they produce probably more oxygen than the Amazon here in Brazil. They produce something like 40% of the oxygen, or fix about 40% of the CO2 we are having. And my colleague Atsuko Tanaka, she wants to know how the pyrenoid is going to change under different CO2 growing conditions. We are not yet so far, and one of the biggest problems why we are not so far is that our Leica high-pressure freezer is working sometimes, most of the times not. So these are high-pressure frozen cells and freeze-substituted. And yeah, that's typical images you are getting. But what we are interested in then is to segment the chloroplast with the pyrenoid, especially, of course, with the pyrenoid, because with the segmentation, then we can define the volume. And so we want to see if how that volume changes. And I guess I have, before I'm going to leave Okinawa, not Okinawa, but before I'm going to leave the institute, probably we have one more shot, and I hope we will get the data. Anyhow, I will stay there from, this is my last trip. After this trip, I will stay there and try my very best to get these things done. Okay, and another thing we were doing again with the university, oh no, wait a minute. Yes, this is again with the University of the Ryukyus. In Okinawa, there is a bacterium which is called Spirochaeta. Oh, I forgot always the family name. Spirochaeta, interrogans. And they are in still waters or in the soil, and they are predominantly excreted by urine from animals and so on. So that's how they can infect, and if you have an open wound or so, they can go into your body, and they love to cross through your kidneys and go to reside in the kidneys and cause illness there. But they also can go to other organs, and in the worst case to the brain, and they can cause death. Also, they don't do it probably too often, as far as I know. So this group was interested in how do they cross the endothelial of the kidney. So these are kidney cells grown on a filter to a monolayer, and then the bacteria is given from underneath of the filter. And as you see here, it can open the tight membranes between the two cells and then creep through the cell barrier into the organ. So this, let's say, were the pictures from our first paper, and then that was let's say, the scheme how things are working. We have another Leptospira, which is Leptospira biflexa, and this is not a pathogen. It cannot cross, you see, it cannot change adherence junction, tight junctions, and so forth, so it cannot go into the kidney. Let's put it easy. I don't know all the different layers it has to cross through. Whereas interrogans does, and then they speculated that it's not only mechanical, that they not only mechanically screw themselves, because as you see it's spiral, it looks like a cork opener, cork screw. So that they screw themselves through the membranes or between the membranes, but that they also influence signal transduction pathway to degrade those junctions, so to degrade adherence junctions, degrade the tight junctions. And then, I don't know where they got the idea, but they got the idea to use proteasomal inhibitor and the lysosomal inhibitor together. And as you see in the next image, they were successful to block them for going through the cell layer. So you could see them coming through the pores into the underneath the cell layer. Some of them managed somehow to go into the cell or in between the cell. Unfortunately, the preparation was not good enough to everywhere see the cell membranes. So sometimes I could easily point them out, but sometimes I was not sure, so we didn't try to model it. And you see they are, here with the down here, maybe inclusion or between down here, but I never saw any bacteria on the upper side. And interestingly, if we did the control experiment without the inhibitors, then it was very difficult to find cells on the filter because many of them went into apoptosis. There was a big opening gap between the cells and so forth. So I had to do 3 or 4 attempts until I found a few cells to prove that, or to have the control to this one. Whereas here the cell layer was really, wherever I wanted to look, there was a monolayer. Okay, so that's the story with the Spirocheta. Then, as Mark showed yesterday, everybody is interested in automated segmentation. I mean, that's the thing. It was also yesterday, it was said today also. We just have too many data nowadays. We have too many data. We have too brilliant data, especially if you look at all the cryo stuff we have seen today. We don't know what it is, where it is, and so forth. So we need algorithm for segmentation. And the lab here in Tokyo, at Tokyo University, they were developing this segmentation software to segment ER in this case, and mitochondria, and in blue you see the contact size. So they want also to know the changes in the contact site if they manipulate some of the proteins within the mitochondria. Another aspect from the same work is this one, that they are looking at the structure of the mitochondrial cristae. So if you have Sheets cristae or if you have tubular cristae, and also here they are working with a protein which I forgot, that is responsible for the cristae to be attached to the, I think, to the inner membrane. So that's, I don't know how far we are going to continue here. The Leptospira project, fortunately, is finished. I don't think I have to do something more over there. But a real great one came up here, and this is from a collaborator indirectly from our university. He is working on clownfish, and he's interested in the chromophores that are in the skin of clownfish. So, you know, they have white pattern, white, black, and orange, and they are from different chromophores. And he also wants to know, of course, in the development, how they are expressed and placed, and of course what they contain. But this is with a collaborator of him from the US, from Virginia University, who sent me this zebrafish fin, and they wanted to see these chromophores here. Actually, they wanted to see this guy here where you see the arrow, and you will see later on. Unfortunately, I missed that one. But you can imagine the challenge you have in such, where do we were? Yeah, doesn't matter. In such a thing, which is actually only about this size, to find those area and to trim you there so that you can do the fibbing there. Okay, so that's a few pictures of the attempts, how to try to go closer to them, to mark them, and then to trim them. Fortunately, we could see them also in the microdome, but not so very well. And now I know that I have to change the microdome because this illumination is not so good as of the other microdome we are having. So with the other microdome illumination, I have more possibilities to see those chromophores. And then I had this volume. It was 10, yeah, it's an Ångström, 10 nanometer by 10 nanometer pixel size, and 20 nanometer fixed sections. And the volume you see over there, it's 60 by 40 by 40. And to take the whole tomogram took 3 weeks of acquisition. And I saw somebody from FEI here. I have to say, this is the best microscope I've ever worked with. I've worked with a lot of Philips FEI Thermo Fisher microscopes, but this is so stable. I mean, imagine it does for 3 weeks. It does cut, turn, go up, take image, go down, cut, turn up, without any stop, without any problems. So anyhow, that's, you see, now I'm looking on the stack. So the image you see here is not the front, which I'm taking the image, but it's the stack looking onto it. And I coarsely indicated the structures I saw just to see where I am, because I didn't know, of course, where I was cutting at the end. And then when you go into the, oh no, I don't have it bigger, but you see over here, these are the area I could FIB, and this unfortunately I missed, and that's the next work which is waiting at home. When I go back, I have to continue with this one. In the meantime, before I came to Europe and Brazil, I did another particle which is white, and in there you will see that this structure is completely filled with guanine crystals. So the guanine crystals diffract the light and give you the white appearance, and they can also be the cause for iridescence in other animals. And guanine crystal, actually, I don't know if you know that, they are also in the skin of chameleon. And because I was working, when I was in Lausanne, I was working on chameleon also. And it was suspected, I don't know how the project progressed, but it was suspected that the distance between those guanine crystal is essential for changing from green to red and back. So I don't know if it works, but the guy I was collaborating with is a friend of my fish guy. So you see how small the world is. Okay, now that's then in the cross section being analyzed. It's not yet finished, but you see in the very dark one we have melanosomes, and here we thought maybe there are guanine crystals in, but with the picture I have seen just now before I came here, I doubt that this is guanine, but that's maybe an emerging particle that loads melanosomes to melanin to get the black color. Okay, this may be a little of interest. I just added it because I got this sample here, this flagella, and the question was what I don't really know what they want to do, but they gave me this flagella, and we wanted to see how much details we can see. And of course I did it as I usually do. I took backscatter electrons on the left, and it was all not really very sharp. And then I recalled my colleague and friend with whom I did my PhD, who is now professor in Ulm, Paul Walter, who was a fan of secondary electrons, and he said at the time, secondary electrons give you the better resolution, and indeed, as you see over here, with the secondary electrons, we can actually see even proteins that are here in between the outer layer of tubulin and the inner layer of tubulin, whereas on the backscatter image it's quite fuzzy. Secondary electrons, however, have the big disadvantage. If you have curtaining, you see it. It's very horrible, and you see also much easier beam damage on the surface. So you have really to work very carefully, or let's put it better in the sense of you have to be lucky. Because probably if it doesn't work, you don't have much means to influence it. So probably, yeah, the best is you have to be lucky. Good. And then I had what was it? The title. The second part was the dream. So now we're coming to the dream. I was doing preliminary experiment with another friend from Tübingen, with Heinz Schwarz, on array tomography. And I hoped actually I can continue with this in Okinawa, but I had nobody really to work on it. I had to do everything on for myself. Let's say this kind of work. They were doing other things for the institute, but if I wanted to do something for myself, I had to do it for myself. So yeah, it never came from, because I put all my energy then in setting up the FIB. That it worked. It took about half a year or so, a bit more, till I had the first real good results, which actually is thanks to Kildare and his team, because they gave me the first sample I could work on, because I didn't have a sample in Okinawa. And today I brought it back to him with the data. Okay, yeah, probably you know this work from Kristina Mikeva, who was taking serial sections on a glass cover, on a glass slide, and then she labeled it fluorescently with, I think, 3 labels at the same time. And as people from biochemistry know, in Western blot, if you want to reuse the Western blot, you can wash it with acid or with high salt, magnesium chloride, for instance, and then you can remove the antibodies and you can start again. And this way she started, and you see she has quite a lot of different antibodies done, and later on you can, of course, all the labels coordinate to each other. So, and what I forgot to say at the end, I don't know, no, I don't have that picture. At the end, you can overlay it with a scanning image, scanning electron microscopy image that gives you the details. So you have then the structure on one section and many different labels, and then you can stack them into the volume. It sounds very easy, but I think it's really time consuming. Anyhow, so yeah. This goes towards array tomography. There are a lot of different approaches. This was one of another collaborator I had very shortly when I was in Lausanne, who developed this technology, and also this diamond knife together with Helmut Gnagi, the president of Diatom Company. And so she could then cut ribbons and place them, as you see over here, on the silicon wafer. Before, a lot of work has been done here with this kind of method, so that the sections were taken up on a 2 millimeter by 1 millimeter hole grid. And a lot of work has been done. For this also one with Sidney Brenner was also already mentioned here. A publication of Sidney Brenner with 340 pages. I think it's a book, one publication, where they were analyzing the whole nervous system of C. elegans. And they did it with this. I think they had 8,000 sections to analyze. I don't know how long they used to it. So that's the let's say, the method they were using, and still quite a lot of people are using. But of course, this is prone to problems. If you happen to touch the film inside with your forceps, or if the grid falls on the floor, then you miss a lot of sections. So you miss immediately a lot of volume. And you can imagine then on the wafer you have much longer ribbons you can select. And if the wafer falls on the floor, it's maybe dirty, so maybe you have to clean it. But it doesn't break usually, and you keep your cells. So that was the idea. And oh yeah. This here you see in comparison, that's that whole 2.1 millimeter hole grid in scale with the silicon wafer, just to get you the idea. So we did, as I said, with Heinz Schwarz, we did some preliminary studies for us where we had not many sections, we had a few. And this is also trypanosoma, so something which is very well researched here. I have not much knowledge about them, so please ask the people in how's it called, Zenobia? They know it. And so Heinz made these sections on cover slips. They were ITO coated, so they were conductive, electrically conductive. And then he labeled them. Actually, he made a quadruple label, as you might see on the next slide. So he labeled them with against the variable surface glycoprotein and against the tubulin underneath the cell membrane with fluorescence and with 2 sizes gold label. Just to start as a proof of principle. And why? Oh, wait a minute. Yeah, we'll be coming back to the trypanosomes. Anyhow, just to show you one of the problems we are having with gold label. I mean, gold label is very interesting if you don't do cryo with template matching, and maybe it doesn't work always. Maybe you still want to use immunogold labeling. Then you see here that it can be very disappointing. So these people here at the University of Zurich, they were interested in labeling a viral protein that they wanted to use for vaccination. This is expressed in a cell. And as we know now, this whole bunch here, every single dot here is a viral protein. And if you look at the gold label, it's not really yellow if you look at it in the electron microscope. I made a big size so that everybody can see it. Then it's very difficult to say what is label, what is background. Whereas if you look at the fluorescence, it's very prominent. So sometimes the fluorescence labeling is very, very badly translated in gold label. Sometimes it's okay, sometimes not. I made the experience with viral proteins. For instance, here in Martin's Reed, I did it with a measles virus. There you saw that the primary antibody binds very nicely because the measles virus we could see in negative contrast. So it was like these brushes you use for cleaning your glassware in the lab. Whereas the gold was here one, here one, here one. For other objects, for other labeling, the gold label is very nicely to work. So this brought us to the idea that we could use fluorescence label to label structures on electron microscopic level. And that's the approach. So we went, or Heinz knew Christian Wurm from Göttingen, who was a specialist on state microscopy. And he did super resolution state images. So again, you see here very nicely the tubulin network in green here. So this is the flagella, which is stained, of course, for tubulin under the membrane, and then the variable surface glycoprotein here covering the flagellar pocket. That's how it can look like in the electron microscope detected with different detectors. And then you see some of them show the gold particle nicer, others show the structure nicer. So this was just to show that we can, let's say that the gold can show the same things as we can see with fluorescence. And here we also made a very interesting discovery. You have seen on the first slide that we had, for instance, 4 sections on the cover slip. And to start with imaging, I first moved, because there are sequential sections, so I used the fluorescence image, not on the section it was taken from, but on the previous section, to adjust all the conditions of the microscope and to see that it works. And then for getting the real data, we went on to the real position where the fluorescence was taken, and then we made a dramatic discovery. There was no gold label, or almost no gold label there anymore. And I don't have the picture, unfortunately, here, but we have pictures where you see from the fluorescence picture is going over the cell, like here, for instance, and on this side, where the fluorescence picture was taken there is almost no gold, and on this side you have a very nice gold label. So you can see that even a STET microscope is able to cause damage, so it was kicking our gold label away. So later on, Christian improved the laser condition so that the loss of gold label was less. Anyhow, so this is then the idea we were thinking of would be nice, and that's what I'm really interested, or would have been interested to continue working on in OIST, to use fluorescent label as a stain for structures in electron microscopy. And with this, we come to something else today. Many times it was people were talking about light microscope in an electron microscope. And again, we are coming back to Rio de Janeiro. Thanks to, I think it was thanks to Kildare, who invited Christoph Kramer, a very well-known light microscopist, and myself to come to Rio for a meeting in Búzios. And first we were parked in a hotel in Rio de Janeiro, and I met Christoph at a breakfast table. Like you see, it's really advantage if you move and if you don't have Zoom meetings, you have to meet people. So we had breakfast together. He invited me to go with him on touristic tours. So we went on the Sugarloaf. We started to talk about microscopy, he light microscopy, I electron microscopy. And he was one of the first really experienced light microscopists who was not saying, we are much better than you. We have super resolution. We get as close in the resolution as you can go in electron microscopy. But he said, no, it's really interesting. We are looking at the same thing, but with different contrasting methods. So we started to continue to discuss, and then we had the idea we should develop something together, and that has become a light microscope, which doesn't exist yet. It's only on paper. There is a patent and calculations, but nobody has yet had. All the companies we contacted didn't have the courage to start using it. So the idea is to have a lensless microscope, which is here, because I said to him, listen, what we need is, we need a very high resolution light microscope in a FIB so that we can cut the lamella where we need it. And the microscopes we have now in the FIB, they have a numeric aperture of something like 0.5, so they're really, in that respect, useless. I mean, the Z resolution is in the micrometer range, and the XY resolution is close to micrometer range, because you cannot get higher resolution objective because of the long working distance. So he suggested then with, we have here Johann von Hase, he is a theoretical physicist, he does all the optical calculations. And Udo Birk is more a practical person. He has ideas how we could construct the instrument. Jan Christoph, he's the father, let's say, of super resolution microscopy. So Stefan Hell, the Nobel Prize winner, was his PhD student. Okay, so the idea is that we have a ring. Maybe take next picture. We have the ring, putting it around the pole piece. And then there are about, one of the calculations is with something like 160 laser beams that they are projected onto this ring and focused, of course, on the focal plane where the sample is. You will need to have another objective, or maybe more than another objective, to collect the photons on the side. But this system defines the numerical aperture. And they calculated that with, we could even apply STED and min flux and so forth, so that we could really go down to at least 100 nanometer lateral resolution, which of course would be much better than what we have nowadays. And as many people pointed out, we can save at least one transfer, which is very helpful for crystal collection, ice crystal collection. Okay, yeah, so I said, Christoph, that I'm going to present this today. So this is the idea. I mean, it's very coarse, of course, but that's how we imagine it should be in the FIB. And that was the original idea, but in the meantime it's sparked off in many other fields. So we could also think of using it in a serial block phase instrument or for array tomography, because also at the Max Planck, in polymer research, there was a professor who was working on graphenes, and he joined now OIST. And these graphenes are fluorescent, they do blinking, so we can use them for super resolution. And one of the collaborators who is now, who is still in Max Planck, she is working a lot now with these graphenes, and she sent a PhD student to my lab for 2 weeks to test how well we could use them for electron microscopy, and they seem to survive quite a lot of our very ugly chemicals, so we could use them for pre-embedding labeling, for instance, and then we can use it for serial block phase to take image and a light image, an electron image, a light image, and so forth. So that's a little bit of a dream. And then somehow Christina, I talked already, she is maybe not the inventor, but definitely she made it famous, the array tomography. She and Martina Schifferer from Munich, they started this Chan Zuckerberg initiative, and I had the feeling I should join them, so at the moment I'm joining them. The idea of it is to promote array tomography, because array tomography probably has some future, and for me it has future in correlation. Not so much what other people showed in getting volumes. For volumes, I would prefer FIB or serial block phase, but there is good reason also to use array tomography. But I see the real potential in array tomography if you combine it with fluorescence. And as you see, in 1 year, there should be a workshop in Munich, and then the year thereafter, next door in Buenos Aires. Okay, and for those who are interested, at the moment we don't have our own website, should come up somewhere end of this year, so, but you could go through this website, which is the volume microscopy community we're setting up, so mainly organized by the British. And with this, I'm at the end, and you see there are a lot of people I have to thank. So let's go to my lab. Gosha, she was starting, or she was always with me from the beginning and helping me where she could. Then she was on a maternity leave, and then I came, and she again did the same as Gosha. She tried to help me a lot. Vincent Laudet is the guy with the fishes, and Rina, she is the one who does all my cryo-electron microscopy. And as you see, there are a lot of other people who helped me to realize a few of the dreams. So, and you, thank you very much. Oh, I forgot the most important slide, this one. Ipe Nife Debiru, which is local language for thank you so much.
Thank you very much, Bruno. So we have time for questions, comments.
Can you say a little more about your latest idea on graphene? How small can you make the crystals? How are you going to make them into binding to specific proteins?
It's not a crystal. It's it looks like unfortunately, I should have had a picture from them. It's like a small piece you have of graphite. You know, it's similar rings. These hexagonal rings, and I don't know how many of them, 10 or something like this. And it might be chemically modified, which I cannot tell you now, but if you want, I can search for the paper to give you the details. So they are really very small. They are bigger than, let's say, a fluorescein molecule, but they are definitely smaller than a quantum dot. And now they were used in organic solutions. But now Akimitsu Narita, that's the guy, he now modified the surface or the outside, let's say, links so that it can be brought into water, and also he put linkers on. So there was one experiment done by another colleague at OIST who was using the click mechanism to label nuclear proteins. I'm really sorry. I love chemistry, I love physics, and I love biology, but everywhere I'm not strong enough for answering all the questions.
Thanks for the talk. And actually, going back all the way to those first very long wavelength light harvesting complexes that show us at the beginning, my question is there any particular chromophore associated to those complexes, or are those just the light absorption is a property of the polypeptide chains themselves?
The chromophore, I mean, the main receptor is the chlorophyll. So
there's a chlorophyll in there.
The magnesium,
Okay.
you know, structure.
Okay.
I don't know, it's not indicated, but these are, let's say, if you have the ring like this, then there are antennas that coming up like this with the chlorophylls. Yes.
Any other questions from the audience? Yeah.
Going back to the graphene, do they emit in different wavelength?
Sorry?
For the graphene particles that John asked you.
I think they are in different wavelengths, like that you would use different sizes. Smaller and bigger, I mean, they're not aggregates, maybe polymers, I don't really know how you call this, sheets. Yeah.
Any other question?
So yeah, Xiao Min, she's no longer here. Xiao Min Liu. I don't know if I have her even on the. Maybe I forgot her on the list. So Xiao Min Liu, who is also working with Christoph. She is working on the stability and all the physical properties of those graphenes.
Okay, so if we don't have any more questions, so we thank again Bruno. And then see you tomorrow, 9 o'clock sharp.